Dynamic graphs, spatiotemporal GNNs. Traditional graph neural networks, GNNs, primarily operate on static graphs, where the nodes, edges, and their attributes remain constant over time. While this assumption simplifies many problems, it fundamentally limits their applicability in scenarios where the underlying relationships and features are inherently dynamic. The real world is rarely static. Objects move, relationships evolve, and conditions change. Modeling these time-varying systems requires a more sophisticated approach. Spatiotemporal GNNs. Why static graph models fall short? Consider a system like a city's traffic network. Roads, edges, and intersections, nodes, are fixed, but the traffic flow, edge attributes like speed or volume, and the presence of vehicles, node attributes or transient edges representing vehicle-to-vehicle communication, change by the second. A static graph model would struggle to capture this fluidity, leading to predictions that are quickly outdated or inaccurate. The limitations of static models become apparent when dealing with evolving relationships. Friendships on a social network form and dissolve. Changing attributes. The temperature at weather stations varies throughout the day. Dynamic structure. New roads are built or temporary closures occur in a transportation network. Physical movement. Autonomous vehicles navigate and interact, constantly altering their relative positions and potential connections. For these reasons, the necessity of dynamic graph models, particularly spatiotemporal GNNs, becomes clear. They provide the framework to represent and learn from data that exhibits both spatial dependencies, relationships between entities, and temporal dependencies, how these relationships and features change over time. Understanding spatiotemporal graphs. A spatiotemporal graph is essentially a sequence of graphs, or a single graph where nodes, edges, and their attributes evolve over time. It captures both the spatial structure, who is connected to whom, and the temporal dynamics, how those connections and attributes change. Conceptual model. Imagine a series of snapshots of a graph, taken at discrete time intervals. Each snapshot represents the state of the graph at a particular moment. Snapshot at $t_0, $g_0 equals v_0, e_0, x_0, Snapshot at $t_1, $g_1 equals v_1, x_1, $1. Snapshot at $k, $g_k rovnítko, v_k, e_k, x_k, a_k, $. Here, $$ represents the set of nodes at time $t$. $_t$ represents the set of edges. $x_t$ represents the node features, and $$ represents the adjacency matrix or edge features. Any of these components can change from one time step to the next. Formal representation. More formally, a dynamic graph can be represented as a sequence of graphs $g equals backslash t backslash t equals 0 $t, where each $t equals t dollar is a static graph at time $t. Alternatively, it can be seen as a single graph with time-varying attributes on its nodes and edges, or even with time-varying connectivity. Time-varying node features. The features associated with a node $v backslash and v$ can change over time, denoted as $x_t. For example, the temperature reading from sensor node. Time-varying edge features. The features associated with an edge $u, v, backslash, and e$ can change over time, denoted as $e_uv_t. For instance, the bandwidth of a network connection. Time-varying connectivity. Edges can appear or disappear over time. For example, two devices connecting or disconnecting. This means the adjacency matrix $t is time-dependent. Time-varying nodes. Nodes themselves can appear or disappear, e.g., a new user joins a platform, a sensor fails. These dynamic elements are what spatiotemporal GNNs are designed to process, enabling them to make predictions or classifications that account for the evolving nature of the data. The challenge of out-of-distribution, OOD, generalization. One of the most significant challenges in modeling dynamic data, especially for predictive tasks, is out-of-distribution, OD generalization. OD refers to a model's ability to perform well on data that comes from a different distribution than the one it was trained on. In static machine learning, OD typically means encountering unseen combinations of features. In dynamic systems, the problem is compounded because the underlying data distribution itself can shift over time. A model trained on historical data from one period might encounter future data where the patterns, relationships, or then the fundamental dynamics of the system have changed. For example, a traffic prediction model trained on rush hour data might perform poorly on holiday traffic patterns, or a disease spread model trained on initial outbreak data might struggle with later stages where public behavior has drastically changed. This is not merely about encountering new data points, but about the rules governing the data having evolved. Spatiotemporal GNNs aim to learn robust representations that can adapt to these shifts, often by learning the underlying dynamics rather than just static correlations. This is a critical factor for deploying models in real-world, continuously evolving environments. Modeling dynamic systems, practical applications. Spatiotemporal GNNs have found widespread utility across various domains due to their ability to capture complex dependencies in dynamic data. Traffic flow prediction, predicting traffic speed and volume across a city's road network, accounting for time of day, special events, and accidents. Nodes are intersections/road segments. Edges are road connections and features like speed and volume change over time. Weather pattern forecasting, predicting temperature, precipitation, or wind speed across geographical regions. Nodes are weather stations or grid cells. Edges represent geographical proximity, and atmospheric conditions are time-varying node features. Spread of diseases across networks. Modeling how a virus spreads through a population. Cons. During individual contacts and travel patterns. Nodes are individuals or communities. Edges represent interactions, and disease status changes over time. Human, animal, or robotic pose estimation and movement prediction. As a running example, predicting the future positions of body joints. This involves tracking how anatomical points move in space and how their relationships, e.g., bone lengths, are maintained or change. Running example, human pose estimation. Human pose estimation is an excellent example of a problem that naturally lends itself to a spatiotemporal graph formulation. It's a relational problem because the human body is a system of interconnected parts, and the movement of one part is inherently related to the movement of others. Framing pose estimation as a relational problem. Nodes, the individual joints or key points of the body, e.g. head, shoulders, elbows, wrists, hips, knees, ankles. Edges, the anatomical connections between these joints representing bones, e.g. an edge between the elbow and wrist representing the forearm. These edges define the skeletal structure. Node features, the 2D or 3D coordinates of each joint at a given time step. Edge features, optional, could represent segment lengths or angles, which might also evolve, e.g., if modeling flexible bodies or changes in perspective. The goal is often to predict the future coordinates of these joints given a sequence of past poses. A GNN is particularly well suited for this because it can 1. Exploit spatial relationships. The graph structure explicitly encodes how joints are connected, allowing the GNN to learn that, for instance, the elbow's movement is constrained by the shoulder and wrist. 2. Capture temporal dynamics. By processing sequences of these graphs, a spatiotemporal GNN can learn the typical motion patterns and predict how the entire pose evolves over time. This involves understanding velocities, accelerations, and kinematic constraints. This approach effectively addresses the challenge of predicting complex, coordinated movements by treating the body as a dynamic graph, where the node's positions change over time while maintaining their underlying anatomical relationships. Illustrative code example, a simple dynamic graph. To solidify the concept of a dynamic graph, let's consider a very simple scenario. tracking the state of a small network of sensors where connectivity and readings change over time. We'll represent our dynamic graph as a list of dictionaries, where each dictionary is a snapshot of the graph at a specific time step. Each snapshot will contain node features and an adjacency list. Code is not spoken. To get code, please see the link in description or bio. This first code chunk defines a helper function code snippet to structure our graph data for each time step. We then use it to define the initial state of our network at code snippet. Here, we have 3 nodes, A, B, C, with distinct sensor readings and specific connections between them. This establishes our baseline static graph at the initial time point. Code is not spoken. To get code, please see the link in description or bio. At code snippet, we simulate a common dynamic scenario, a change in node features. In this case, the temperature reading at node has increased. Notice that the structure of the graph, which nodes exist and how they are connected, remains constant, but the attribute associated with a node has evolved. This highlights how node features can be time-varying. Code is not spoken. To get code, please see the link in description or bio. Moving to code snippet, we demonstrate a change in the graph's connectivity. The edge between node B and node C has disappeared, implying that C is now isolated from B. This could represent a link failure or a sensor going offline. This showcases how the adjacency matrix or edge list can be dynamic, reflecting changes in relationships or physical connections. Code is not spoken. To get code, please see the link in description or bio. Finally, at code snippet, we illustrate a more complex dynamic, the addition of a new node, D, and further evolution of existing node features. Node D is introduced into the network and immediately connects to node. Furthermore, node not only updates its temperature reading, but also acquires a new feature, humidity. This progressive example clearly demonstrates how nodes, edges, and features can all change over time, forming a sequence of distinct graph snapshots that a spatiotemporal GNN would learn from. This simple example provides a concrete understanding of how a dynamic graph evolves, laying the groundwork for understanding how spatiotemporal GNNs process such complex, time-varying data. Temporal models, relations through time. Real-world phenomena rarely occur in isolation or remain static. From the intricate movements of molecules to the sprawling dynamics of social networks, time is an inherent dimension that profoundly influences relationships and states. While the preceding discussions have largely focused on static graphs and their analysis, understanding and modeling these evolving systems necessitates a transition to dynamic graphs and temporal modeling. The imperative of temporal dynamics. Many critical real-world problems are fundamentally dynamic, meaning that the entities involved, their attributes, and the relationships between them change over time. Ignoring this temporal aspect can lead to incomplete or inaccurate models, limiting their predictive power and applicability. Consider a few examples. Traffic flow prediction. Roads, intersections, and vehicles form a complex network. Traffic patterns, flow, speed, change drastically throughout the day, influenced by time-dependent factors like rush hour, events, or weather. A static model would fail to capture these crucial temporal variations. Social network evolution. Friendships form and dissolve, interests shift, and communities emerge or fragment. Analyzing a social network at a single point in time misses the story of how relationships evolve, impacting information diffusion, trend prediction, or community detection. Disease spread modeling. The progression of an epidemic depends not on the current connectivity of individuals, but also on how contact networks change over time, e.g., due to interventions, seasonal changes, or travel restrictions. Financial fraud detection. Fraudulent activities often involve sequences of transactions and evolving patterns of behavior. A static snapshot of a transaction graph might miss the subtle, time-dependent anomalies that signal illicit activity. In each of these scenarios, the underlying graph structure, its nodes, edges, and their associated features, is not fixed but rather a fluid entity, constantly adapting to new information and interactions. Dynamic graphs versus spatiotemporal graphs. The terms dynamic graph and spatiotemporal graph are often used interchangeably, but it's helpful to clarify their nuances in this context. Dynamic graph. This is the broader term, referring to any graph whose structure or features change over time. Changes can include node dynamics, nodes appearing or disappearing, e.g., users joining/leaving a platform. Edge dynamics, edges forming or dissolving, e.g., new friendships, broken connections. Node/edge attribute dynamics, features associated with nodes or edges changing values, e.g., a user's activity level or road congestion. Spatiotemporal graph. This term emphasizes that the changes are influenced by both space, the graph structure itself, representing spatial relationships, and time. Many real-world dynamic graphs are inherently spatiotemporal. For instance, traffic flow involves vehicles moving through a spatial road network over time. Human pose estimation involves body parts, spatial arrangement, moving and interacting over time. In the context of GNNs, when we refer to temporal models or dynamic graphs, we are generally dealing with spatiotemporal data where the graph structure and/or features evolve over time, and the learning objective involves understanding or predicting these evolutions. Modeling dynamic graphs, a toy example. To solidify the concept of a dynamic graph, let's consider a very simple social network where friendships evolve over 2 time steps. We can represent our network using an adjacency list or, more conveniently for demonstration, a graph library like code snippet. Code is not spoken. To get code, please see the link in description or bio. This initial code block imports code snippet and code snippet for graph creation and visualization. It also defines a helper function code snippet to render our network snapshots, ensuring a consistent visual layout across different time steps for easier comparison. Now, let's define our social network at code snippet. Code is not spoken. To get code, please see the link in description or bio. At code snippet, we initialize a graph code snippet with 3 friendships: Alice Bob, Bob Charlie, and Charlie David. A new person, Eve, has joined the network but hasn't formed any connections yet. This demonstrates that nodes can exist without edges. Next, we simulate. Changes at code snippet. Code is not spoken. To get code, please see the link in description or bio. At code snippet, we create code snippet by copying code snippet to represent its evolution. We then introduce a new friendship between Eve and Alice, demonstrating an edge formation. The friendship between Bob and Charlie dissolves, illustrating an edge removal. Finally, a new node, Frank, joins and immediately forms a connection with David, showcasing both node and edge addition. This simple example clearly shows how nodes and edges can change over time, forming a dynamic graph. How GNNs incorporate time. The core challenge in dynamic graph modeling is to extend the message passing paradigm of GNNs to account for temporal dependencies. While static GNNs learn representations based on a fixed graph structure, dynamic GNNs must learn from a sequence of graphs or from continuously evolving graphs. Several high-level strategies are employed. 1. Recurrent connections on graph embeddings. One common approach is to treat the sequence of graph snapshots as a sequence of inputs to a recurrent neural network, RNN. At each time step, a standard GNN processes the current graph snapshot to generate node or graph embeddings. These embeddings are then fed into an RNN, like an LSTM or GRU, which learns to capture temporal dependencies by maintaining a hidden state that propagates information across time steps. Code snippet temporal GNN encode snippet_sequence code snippet. They generate sequence code snippet sync code snippet code snippet. 1. T2. Code snippet steps code snippet past spatial outputs code snippet spatiotemporal and layer code snippet self spatial encode snippets nv 1 code snippet self temporal code snippet code, snippet dynamic graph predictor code, snippets underscore code, snippet underscore x underscore code, snippet predicted underscore x underscore t underscore plus underscore, one code, snippet code, snippet. One temporal. Physical constraints. The model can learn that certain joint angles are physically impossible or that joint distances should remain relatively constant. Trajectory prediction. Predict future joint positions, allowing for smoother animations, motion forecasting in robotics, or early detection of abnormal movements in medical applications. By representing the human body as a dynamic graph, GNNs can leverage their ability to learn from both local relational structures and global temporal patterns, leading to more accurate and robust pose estimation, which is vital in fields ranging from robotics to filmmaking and virtual reality. Problem definition. Pose estimation. Pose estimation is a fundamental problem in computer vision and machine learning that involves determining the position and orientation of an object, often a human body, within an image or video sequence. When dealing with dynamic entities like a moving person, this problem extends beyond static snapshots to predicting future movements, a task known as path prediction or trajectory forecasting. This section precisely defines pose estimation as a dynamic relational problem, laying the groundwork for understanding how spatiotemporal graph neural networks, GNNs, are uniquely suited to address it. The dynamic nature of pose estimation, path prediction. Human movement is inherently dynamic. It's a continuous flow of positions and configurations over time, not a series of isolated static poses. For this reason, accurately modeling and predicting human motion requires considering the temporal dimension. Path prediction, in this context, refers to forecasting the future trajectory of individual body joints or the entire body configuration based on a sequence of past observations. Consider a single point moving in a 2D space. If we observe its coordinates code snippet at several past time steps, we could try to predict its next position. This simple concept scales to complex human movements where each body joint, e.g., elbow, knee, ankle, has its own trajectory, and these trajectories are interdependent. To illustrate the fundamental idea of path prediction, let's consider a basic numerical example of a single point's movement. Code is not spoken. To get code, please see the link in description or bio. This code snippet generates a simple 2D path where a point moves linearly. Imagine we observe the first code snippet time steps of this path and want to predict the code snippet time step. This is the essence of path prediction, using historical data to forecast future states. Code is not spoken. To get code, please see the link in description or bio. This simplified example demonstrates the core idea. By analyzing past data, the code snippet, we can infer patterns like velocity and use them to forecast future states, code snippet. For human pose estimation, this concept expands to predicting the coordinates of multiple joints simultaneously, often for several future frames. The relational nature of pose estimation, body as a graph. Beyond being dynamic, human movement is deeply relational. The movement of one body part is intrinsically linked to others. For instance, the elbow's position depends on the shoulder's position, and the knee's movement affects the ankle. This interdependency forms a natural graph structure. Nodes, individual body joints, e.g. head, neck, shoulders, elbows, wrists, hips, knees, ankles. Edges, the anatomical connections or bones between these joints, e.g. shoulder to elbow, hip to knee. This relational structure means that a GNN can learn not just the individual trajectories of joints, but also how their movements are coordinated and constrained by the underlying skeletal structure. This is crucial for realistic and physically plausible pose predictions. Dataset for pose estimation. CMU Motion Capture Database. To train and evaluate models for human pose estimation and path prediction, a robust dataset of human motion is essential. A widely used resource for this purpose is the CMU Motion Capture Database. This dataset contains a vast collection of high-resolution motion capture data, recorded using optical motion capture systems. The data typically consists of sensor data, raw readings from markers placed on a human body. In the context of a CMU motion capture database, this often refers to the 3D positions of reflective markers attached to specific anatomical landmarks. While the general analysis mentions 41 sensors, this typically refers to the number of markers whose 3D coordinates are recorded over time. Each marker corresponds to a specific point on the body. Frames. The data is recorded as a sequence of frames, where each frame represents the 3D positions of all markers at a specific point in time. This creates a time series of pose data. Pre-process segmentation. Before using the raw motion capture data, it often undergoes pre-process segmentation. This typically involves marker labeling, identifying which marker corresponds to which body part. Gap filling, interpolating missing marker data due to occlusions or sensor. Dropouts, noise reduction, smoothing out minor fluctuations in marker positions. Segmentation of actions/subjects, dividing the continuous motion capture stream into distinct actions, e.g., walking, running, dancing, or separating data from different subjects. This ensures that each sequence provided for training is a coherent movement segment. Mapping sensor data to graph structure. Let's clarify how the raw sensor, marker, data from the CMU motion capture database translates into the nodes and edges of our graph representation. Each of the 41 sensors, markers, corresponds to a specific anatomical landmark or joint on the human body. While the exact mapping can vary slightly depending on the specific capture setup, a common interpretation would be sensor/marker location corresponding body part/joint. Head top, forehead head. Left/right shoulder shoulder, L/R. Left/right elbow elbow, L/R. Left/right wrist wrist, L/R. Left/right hip hip, L/R. Left/right knee knee, L/R. Left/right ankle ankle, L/R. Left/right to, L/R. Spine base, spine mid-pelvis, spine. Additional markers for fingers, neck, etc. These marked locations, typically represented by their 3D coordinates code snippet at each time step, become the nodes of our graph. The edges between these nodes are defined based on the known anatomical structure of a human skeleton. These are typical, Y-fixed, and represent the bones connecting the joints. For instance, there's an edge between the shoulder and the elbow, representing the upper arm bone, and another between the hip and the knee, representing the thigh bone. Here's a conceptual Python representation of how a single frame of pose data might be structured and how its relational graph could be defined, using a simplified skeleton for clarity. Code is not spoken. To get code, please see the link in description or bio. This dictionary represents the code snippet of our graph for a single time step, with their spatial attributes, 3D coordinates. Code is not spoken. To get code, please see the link in description or bio. This conceptual code demonstrates how the anatomical structure of the human body naturally forms a graph. The nodes are the joints with their 3D coordinates as features, and the edges represent the fixed bone connections. This graph structure is static, while the node features coordinates change over time. Problem formulation for path prediction. Given a sequence of code snippet past frames of human pose data, represented as a sequence of graphs code snippet, where each code snippet contains the 3D coordinates of all joints at time step code snippet. The goal of path prediction is to predict the 3D coordinates of all joints for the next code snippet future frames. Code snippet. This can be formally stated as learning a function code snippet. Code snippet. The challenges in solving this problem include high dimensionality. Each frame involves the 3D coordinates of many joints, e.g., 41 markers 3 dimensions equals 123 values per frame. A sequence of frames quickly becomes a very high-dimensional input. Complex nonlinear dynamics. Human movement is highly nonlinear, making it difficult to model with simple linear prediction methods. Temporal dependencies. The movement at any given time is highly dependent on previous movements and velocities. Relational constraints. The physical structure of the human body imposes strong constraints on how joints can move relative to each other. For example, an elbow cannot move independently of the shoulder and wrist. Occlusions and noise. Real-world motion capture data can be noisy or have missing data due to occlusions, requiring robust models. By framing pose estimation as a dynamic relational problem and leveraging graph structures, spatiotemporal GNNs can effectively capture both the temporal evolution of movements and the inherent spatial relationships between body parts, leading to more accurate and physically plausible predictions. Setting up the problem. From human motion to dynamic graphs. The task of dynamic pose estimation, which involves tracking the 3D configuration of a human body over time, presents a compelling challenge that is naturally suited for graph-based modeling. Understanding how to translate this real-world problem into a computational framework is the first crucial step in developing an effective solution. Formulating dynamic pose estimation as a graph problem. At its core, the human body can be conceptualized as a kinematic chain, where various body parts are interconnected. This inherent structure aligns perfectly with the definition of a graph. Joints as nodes. Each significant anatomical joint, e.g. wrist, elbow, shoulder, hip, knee, ankle, is represented as a node or vertex in the graph. These nodes typically carry attributes such as their 3D coordinates, code snippet, and potentially other kinematic properties like velocity or acceleration. Skeletal connections as edges. The natural connections between these joints, representing bones or segments of the body, e.g. shoulder to elbow, hip to knee, form the edges in the graph. These edges signify a direct spatial or structural relationship between two nodes. Edges can be directed or undirected, depending on the specific problem formulation, e.g., a parent-child relationship in a kinematic tree versus a simple connection. For dynamic pose estimation, this graph representation is not static. STH. A human body moves, the positions of the joints change, and, consequently, the graph itself evolves over time. This leads to the concept of a dynamic graph, where the node attributes, joint coordinates, are updated at each time step, and occasionally, even the graph topology connections might change, though for human pose, the skeletal structure typically remains constant. Consider a single frame of human pose data. We can represent it using a simple Python class structure. Code is not spoken. To get code, please see the link in description or bio. The code snippet class encapsulates the identity and 3D position of a single joint. The code snippet class then aggregates these code snippet objects as nodes and defines the code snippet edges between them, representing the skeletal structure. The code snippet and code snippet methods illustrate how this conceptual structure could be translated into a format suitable for graph processing libraries, where nodes are often represented by numerical indices and their associated features. Let's instantiate a very basic skeleton for a single pose. Code is not spoken. To get code, please see the link in description or bio. This code snippet demonstrates how a snapshot of human pose, represented by code snippet, becomes a graph where each code snippet is a node and the code snippet defines the edges. This graph structure explicitly encodes the spatial relationships between body parts. Why graph neural networks? Capturing spatiotempo. RAL relationships. The explicit graph structure of human pose makes graph neural networks, GNNs, a highly suitable choice for this problem. Unlike traditional neural networks that operate on flat vectors, GNNs are specifically designed to process data residing on graphs, leveraging the connectivity information. GNNs excel at learning relational dependencies. GNNs propagate information across the graph's edges, allowing them to learn how the position of one joint, e.g., the elbow, is inherently linked to its connected joints, shoulder and wrist. This is crucial for understanding kinematic constraints and plausible body configurations. Handling varying topologies. If applicable, while human skeletal topology is largely fixed GNNs can inherently adapt to graphs with different numbers of nodes or connections, making them versatile for other graph-based problems. For dynamic pose estimation, we are dealing with a sequence of these code snippet instances over time. This requires GNN architectures that can handle both spatial, within a single graph, and temporal, across a sequence of graphs, dependencies. Such models are often referred to as spatiotemporal graph neural networks, SDGNNs. These can take various forms, including recurrent GNNs, RGNNs integrating recurrent units, like LSTMs or GRUs, with graph convolution operations to process graph sequences. Attention-based GNNs, using attention mechanisms to weigh the importance of different neighbors or different time steps, allowing the model to focus on relevant information. Temporal graph convolutional networks, TGCNS, combining graph convolutions with 1D temporal convolutions to capture patterns across both space and time. The problem then becomes predicting the next code snippet or a sequence of future code snippet, given a history of observed code snippet instances. Code is not spoken. To get code, please see the link in description or bio. This code snippet function generates a list of code snippet objects, each representing a pose at a different time step. This list forms the dynamic graph sequence that a spatiotemporal GNN would process to predict future poses. The crucial role of benchmarking. While GNNs offer a powerful paradigm for relational data, it is imperative to benchmark their performance against alternative, non-graph methods. Benchmarking serves several critical purposes. Validation. It provides a quantifiable measure of how much improvement, if any, the GNN-based approach offers over simpler or established methods. Understanding strengths and weaknesses. By comparing, we can discern where the GNN truly excels, e.g., handling complex interactions, and where its advantages might be marginal. Establishing a baseline. A well-chosen benchmark sets a baseline performance level. Any proposed new model must significantly outperform this baseline to be considered a valuable contribution. Choosing a non-graph baseline, a sequential model, for dynamic pose estimation. A suitable non-graph benchmark is a sequential model that processes the joint coordinates as a flattened time series. A common choice would be a recurrent neural network, RNN, such as an LSTM, long short-term memory, or GRU, gated recurrent unit, or even a simple multilayer perceptron, MLP, applied independently to each time step or concatenated over a window. Consider a simple MLP or RNN that processes the joint coordinates without explicitly understanding their graph structure. It would treat the 3D coordinates of all joints at a given time step as a single, long feature vector. Code is not spoken. To get code, please see the link in description or bio. In the code snippet and code snippet examples, the input code snippet for a single pose frame would be a flattened vector of all joint coordinates, code snippet. While these models can learn temporal correlations, especially the RNN, they inherently struggle with the spatial relationships between joints. For instance, if a person crosses their arms, an MLP or RNN might struggle to interpret the relative positions of the hand and shoulder joints if they are close in 3D space, but distant in the kinematic chain. The model would have to implicitly learn these complex geometric constraints from vast amounts of data, without the explicit structural guidance provided by a graph. In contrast, a GNN-based model would process the data as a graph sequence, where the explicit edges between joints directly inform the message passing. Mechanism. Code is not spoken. To get code, please see the link in description or bio. The code snippet model, even in its simplified placeholder form, highlights the fundamental difference. It would directly consume graph structured data via code snippet objects, allowing it to leverage the code snippet for explicit relational reasoning. This makes GNNs inherently more robust to scenarios like occlusions or complex limb configurations where the spatial relationships are paramount. Setting up the problem with this explicit graph structure and a clear non-graph baseline allows for a rigorous evaluation of the benefits of GNNs in dynamic pose estimation. This section delves into the practical aspects of setting up a dynamic graph-based learning problem, specifically focusing on human pose estimation. It bridges the theoretical problem definition with the concrete steps required to prepare real-world data for machine learning models, particularly those leveraging graph neural networks, GNNs. Data source: the CMU Motion Capture Database. The foundation for this problem setup is the well-known CMU Motion Capture Database. This extensive dataset is a standard benchmark in human motion analysis, widely used for research in areas such as character animation, human activity recognition, and pose estimation. It contains a vast collection of human motion sequences, captured using optical motion capture technology, providing high-fidelity spatial data over time. For our pose estimation task, we primarily interact with two types of files from this database. Code snippet: a claim skeleton file, defines the hierarchical structure of the skeleton, including joint names and their connectivity. It also contains information about the initial, reference, pose, and the positions of the motion capture markers, sensors, relative to specific body segments. Code snippet: a claim motion capture file contains the actual motion data as a sequence of joint angles and root translation/rotation for each frame, corresponding to the skeleton defined in code snippet file. While the full code snippet file can be complex, for this problem, we are primarily interested in extracting the spatial coordinates of specific sensors, markers, attached to the body. Understanding raw sensor data. The code snippet format snippet. The raw sensor data, as presented in its textual code snippet format, provides the foundational input for our feature engineering process. Each line pertinent to sensor data typically includes a label identifier for the sensor and its three-dimensional XYZ coordinates in a given frame. Consider a simplified representation of the code snippet data structure for sensor positions. Code is not spoken. To get code, please see the link in description or bio. This snippet conceptually illustrates how sensor labels and their corresponding XYZ coordinates are structured. In practice, the exact marker positions are often derived from the code snippet files combined with the code snippet skeleton or pre-processed into a more direct format for machine learning tasks. For this problem, we'll assume a stream of XYZ coordinates for each sensor over time. Parsing raw sensor data. The first practical step is to parse this raw, text-based data into a structured format that can be easily manipulated by Python. A common approach is to load it into a data structure like a list of dictionaries or a pandas data frame. Let's consider a simplified scenario where we have a file containing sensor data per frame, similar to a CSV. Imagine a file named code snippet with content like this. Code is not spoken. To get code, see the link in description or bio. We can parse this file into a pandas data frame for easy manipulation. Code is not spoken. To get code, please see the link in description or bio. This initial parsing step converts the raw text data into a structured code snippet, where each row represents a sensor's position at a specific frame. This format is far more convenient for subsequent feature engineering. Feature engineering, from positions to spatiotemporal features. Raw XYZ coordinates provide spatial information, but for dynamic graph analysis and predicting future poses, we also need to capture temporal dynamics. This is achieved by deriving additional features, specifically velocity. Spatial positions, XYZ coordinates. The most direct features are the three-dimensional coordinates, code snippet, code snippet, code snippet, of each sensor at every time step. These represent the spatial location of the sensor marker in 3D space. Velocity calculation, change in position. Velocity is a critical feature that captures the rate and direction of movement. For each sensor, its velocity can be calculated by determining the change in its position between consecutive frames. While sophisticated methods exist for computing motion, e.g., accounting for angular rotations and global translational movements of the entire body, for individual sensor velocity, a simple finite difference approach is often sufficient. The velocity for a sensor at time code snippet can be approximate. ds $$ x t equals backslash frac x t x t1 backslash delta t dollar dollar. Dólar dólar v guión bajo y t igual a barra inversa frac y t guión bajo inversa delta t dólar dólar. Dólar dólar v potržítko z t rovnítko frac levá složená závorka s 1 pravá složená závorka levá složená závorka delta t pravá složená závorka dolar dolar. Where $x, t, dollar, dollar y, t dollar, dollar z, t dollar are the coordinates at timecode snippet, and dollar backslash delta t dollar is the time difference between frames, often assumed to be one if frames are equally spaced. Let's expand our code snippet to include velocity features. We'll need to group by code snippet to calculate velocities independently for each sensor. Code is not spoken. To get code, please see the link in description or bio. This code snippet effectively calculates the velocity components for each sensor. The code snippet ensures that the code snippet operation is performed independently for each sensor's time series, preventing erroneous calculations across different sensors. The code snippet assigns a zero velocity to the first frame of each sensor sequence, as there's no preceding frame to calculate a difference from. Constructing the 6 features per sensor. By combining the spatial coordinates code snippet, code snippet, code snippet with their corresponding velocities code snippet, code snippet, code snippet, we arrive at 6 distinct features for each sensor at every time step. These 6 features comprehensively describe both the static position and the dynamic movement of each sensor within the 3D space. For a sequence of 50 frames and given 31 sensors, this means our input data for a single motion sequence would be a tensor shapecode. Snippet. This multidimensional array is the standard format for spatiotemporal models. Graph representation, nodes, edges, and adjacency. A crucial aspect of dynamic graph learning is explicitly defining the graph structure. In our human pose estimation problem, nodes, each of the 31 sensors, motion capture markers, attached to the human body serves as a node in our graph. These sensors are typically placed at key anatomical landmarks. Edges. Edges represent the physical connections or relationships between these sensors. For human pose, these connections naturally follow the skeletal structure, e.g., a sensor on the elbow is connected to a sensor on the wrist and another on the shoulder. The graph is undirected. Connection from A to B implies connection from B to A. And unweighted, all connections are treated equally in strength. The edge data, defining these connections, is typically provided as part of the dataset, often in a separate file or within the code snippet file skeleton definition. It's not inferred from the raw sensor data itself, but rather represents the inherent anatomical structure. Representing the graph, adjacency matrix. The most common way to represent the graph structure numerically is through an adjacency matrix. For a graph with code snippet nodes, the adjacency matrix code snippet is in code snippet matrix where code snippet if there's an edge between node code snippet and node code snippet and code snippet otherwise. Since our graph is directed, the adjacency matrix will be symmetric code snippet. Let's assume we have a list of edges representing the connections between our 31 sensors. For example, if sensor 0 is connected to sensor 1, and sensor 1 to sensor 2, etc. Code is not spoken. To get code, please see the link in description or bio. This code snippet demonstrates how to construct an adjacency matrix from a list of edges. Each code snippet tuple in code snippet represents a connection between sensor code snippet and sensor code snippet. The resulting code snippet is a direct numerical representation of the graph's topology, which is essential input for graph neural networks. Data discrepancies and clarifications. It's common in large data sets like CMU mocap for different research papers or subsets to use varying numbers of sensors or trials. 31 versus 41 sensors. While the CMU motion capture database can include up to 41 markers on the body, many studies, including the NRI paper this problem is based on, choose to focus on a subset of these markers. The 31 sensors mentioned likely correspond to specific key anatomical landmarks that are consistently tracked and relevant for the pose estimation task, simplifying the problem while retaining sufficient information. 31 examples versus 33 trials. Examples typically refer to distinct motion sequences or actions, e.g., 31 different ways of walking, running, or jumping. Trials could refer to individual recordings or repetitions of these examples. As possible that 31 distinct motion types were recorded, with some examples having multiple trials or repetitions, leading to a slightly higher total count of individual recordings, 33 trials. This is standard practice in motion capture datasets to account for variability. The critical importance of correct graph structure. One of the most significant takeaways from setting up this problem is the absolute necessity of an explicitly defined and correct graph structure. When working with sensor data from a human body, it's tempting to treat each sensor's time series independently, perhaps using a simple recurrent neural network, RNN, or a convolutional neural network, CNN, across the time dimension for each sensor. However, this approach ignores the inherent physical connections and interdependencies between body parts. An incorrect or inferred graph structure, e.g., based on simple proximity, can be detrimental. Loss of relational information. If the model doesn't know that the left knee sensor is connected to the left hip and left ankle sensors, it misses crucial contextual information about how these parts move relative to each other. Suboptimal feature learning. GNNs are designed to aggregate information across connected nodes. Without a precise graph, the aggregation process will be flawed, leading to suboptimal feature representations. Poor generalization. Explicit graph structures, especially those reflecting anatomical reality, are vital for out-of-distribute. Tie-in. OOD generalization. A model trained on one person's movements can better generalize to another person's movements if it understands the underlying, consistent skeletal topology, rather than try to learn spurious correlations from raw spatial data alone. The graph provides a structural inductive bias that helps the model understand the physical constraints of human movement. By explicitly providing the adjacency matrix that represents the anatomical connections between sensors, we enable the graph neural network to effectively learn spatiotemporal relationships, leading to more accurate and robust pose estimation. This contrasts sharply with non-graph approaches that treat sensor data as independent time series, which would struggle to capture the complex, coupled dynamics of human motion. Building models with memory. In the previous sections, we established the problem of dynamic pose estimation and prepared our sequential pose data. However, traditional feed-forward neural networks, which process each input independently, are ill-suited for sequences. They lack the ability to retain information from previous time steps, effectively treating each frame of a motion sequence as an isolated data point. To capture the temporal dependencies inherent in human motion, our models must possess memory, the capacity to leverage past information to understand and predict future events. The concept of memory in neural networks. The idea of memory in neural networks for sequential data is realized through recurrent connections. Unlike feed-forward networks where information flows strictly in one direction, recurrent networks feed the output, or a derivative of the output, of a neuron or layer back into itself as input for the next time step. This creates a loop, allowing the network to maintain an internal state, often referred to as a hidden state, that encapsulates information from the entire sequence process so far. Consider predicting the next word in a sentence. To predict river, after the boat sailed down, the model needs to remember boat and sailed to understand the context. Similarly, in pose estimation, predicting the next joint position requires knowledge of previous joint positions and their velocities. Recurrent neural networks, RNNs. The founda. Final model for sequential data is the recurrent neural network, RNN. At each time step code snippet, an RNN takes the current input code snippet and the hidden state from the previous time step code snippet to compute a new hidden state code snippet and an output code snippet. Mathematically, a simple RNN's hidden state update can be expressed as code snippet and the output as code snippet. Here, code snippet represents weight matrices, and code snippet represents bias vectors. The code snippet activation function introduces nonlinearity. This simple structure allows information to propagate through the sequence, theoretically enabling the network to learn long-term dependencies. The vanishing gradient problem. Despite their conceptual elegance, vanilla RNNs suffer from a significant practical limitation, the vanishing gradient problem. During backpropagation through time, BPT, the gradients used to update the network's weights can become extremely small as they propagate backward through many time steps. This occurs because gradients are repeatedly multiplied by weight matrices, and if these weights are small, the gradients can exponentially shrink, effectively preventing the network from learning long-term dependencies. For instance, an event that happened 100 time steps ago might have almost no impact on the current gradient calculation, meaning the network forgets distant past information. Conversely, the exploding gradient problem can occur if gradients become too large, leading to unstable training, though this is often mitigated by gradient clipping. Gated recurrent units, GRUs. To address the vanishing gradient problem and better capture long-term dependencies, more sophisticated RNN architectures like long short-term memory, LSTM, networks, and gated recurrent units, GRUs, were developed. Both introduce gates, specialized mechanisms that control the flow of information into and out of the recurrent unit, allowing them to selectively remember or forget information. GRUs are a simplified version of LSTMs, offering a good balance between performance and computational efficiency. They have two primary gates. 1. Update gate. Code snippet. This gate decides how much of the past hidden state, code snippet, should be carried over to the current hidden state, code snippet, and how much of the new candidate hidden state, code snippet, should be incorporated. It's like a blend factor. 2. Reset gate. Code snippet. This gate determines how much of the previous hidden state, code snippet, should be forgotten when calculating the new candidate hidden state, code snippet. A low value means the previous state is largely ignored, allowing the model to focus on the current input. By using these gates, GRUs can maintain a memory of relevant information over long sequences, bypassing the vanishing gradient issue. For our pose estimation task, we will use a GRU-based model as our non-graph-aware baseline. This will demonstrate the performance of a purely temporal model before we explore how incorporating graph structures can further enhance predictions. Implementing a recurrent model in PyTorch. We will define a PyTorch code snippet class for our recurrent model. This model will take a sequence of pose data as input and output a prediction for the next pose in the sequence. Code is not spoken. To get code, please see the link in description or bio. The code snippet class initializes a GRU layer, code snippet, and a fully connected linear layer, code snippet. The code snippet method sets up these components, taking code snippet, code snippet, code snippet, code snippet, and code snippet as parameters. Code snippet refers to the number of features per time step, e.g., total number of joint coordinates in a pose. Code snippet is the dimensionality of the GRU's internal hidden state. Code snippet is the size of the predicted output, e.g., the same as code snippet if predicting the next full pose. The code snippet method defines the computation flow. It first initializes the hidden state code snippet as zeros, matching the required dimensions for the GRU. Then, the input code snippet and code snippet are passed to the code snippet layer. The code snippet layer returns two tensors, code snippet, which contains the hidden state for each time step in the input sequence, and code snippet, which is the final hidden state across all layers for the last time step. For sequence to one prediction, predicting the next frame. From a sequence, we take the hidden state of the last time step, code snippet, and pass it through the final linear layer, code snippet, to get our prediction. Data preparation and setup for training. Before training, our data needs to be properly formatted and normalized. Pose data, consisting of joint coordinates, typically has varying scales. Min-max scaling is a common normalization technique that transforms features to a fixed range, usually code snippet, which helps neural networks converge faster and more stably. Data normalization example. Assuming your pose data code snippet is a number py array where each row is a pose and columns are features. Code is not spoken. To get code, please see the link in description or bio. Normalization ensures that no single feature dominates the learning process due to its larger numerical range. Setting up data loaders, optimizer, and loss function. For efficient training, data is typically loaded in batches using PyTorch's code snippet. We'll also define our optimizer and loss function. Code is not spoken. To get code, please see the link in description or bio. We define key hyperparameters like code snippet, and code snippet. The code snippet is set to CUDA if a GPU is available, otherwise CPU. Code snippet is chosen as the loss function because pose estimation is a regression problem, predicting continuous joint coordinates. The code snippet optimizer is a popular choice for its adaptive learning. G-rate capabilities. A code snippet scheduler is included to dynamically adjust the learning rate during training, which can help achieve better convergence. Training loop. The training loop is the core of the deep learning process, iteratively refining the model's parameters. Code is not spoken. To get code, please see the link in description or bio. The training loop iterates for a specified number of code snippet. Each epoch consists of a training phase and a validation phase. Training phase. Code snippet sets the model to training mode, enabling dropout and batch normalization updates. Code snippet clears gradients from the previous optimization step. T adjusts the learning rate based on the validation loss. If the validation loss stagnates, the learning rate is reduced, helping the model find a better minimum. Early stopping. This mechanism prevents overfitting. If the validation loss does not improve for a predefined number of code snippet epochs, training is halted. This saves computational resources and helps select a model that generalizes well to unseen data. Testing and autoregressive prediction. After training, the model's performance is evaluated on a separate test set. For sequence prediction tasks like pose estimation, we often perform autoregressive prediction. This means the model predicts the next frame, and then that predicted frame is fed back into the model as part of the input sequence to predict the subsequent frame. This mimics real-world scenarios where future ground truth data is unavailable. Code is not spoken. To get code, please see the link in description or bio. The testing loop operates slightly differently from training. 1. Code snippet and code snippet. Essential for consistent evaluation. 2. Autoregressive process. We start with encode snippet sequence, e.g., the first 10 frames of a motion clip. The model predicts the next frame based on this code snippet. The predicted frame is then code snippet to a list of code snippet. Crucially, the code snippet is updated. The oldest frame is removed, code snippet, and the newly predicted frame, code snippet, is appended at the end. This slides the input window forward, allowing the model to make subsequent predictions based on its own generated output. This process repeats with a desired code snippet, e.g., the length of the full target sequence. 3. Loss calculation. The loss is calculated for the entire sequence of code snippet against the code snippet. 4. Data collection. Predicted and true sequences are stored, often converted to number py arrays for later analysis or visualization. Interpreting results and model limitations. For regression tasks like pose estimation, accuracy is typically measured by how close the predicted values are to the ground truth. Metrics like mean squared error, MSE, or mean absolute error may quantify the average error magnitude. A lower MSE indicates better prediction quality. If accuracy figures, e.g., 70%, are mentioned, they usually refer to a custom metric, such as the percentage of predicted frames whose error falls below a certain threshold. It's crucial to clarify such custom metrics for precise interpretation. While GRUs effectively handle temporal dependencies, they have inherent limitations for problems like pose estimation. Lack of relational understanding. GRUs process pose data as a flat vector of joint coordinates. They do not inherently understand the anatomical structure of a human body, e.g., that the knee is connected to the hip and ankle. This means they struggle to enforce physical constraints or leverage the natural graft structure of the ski. Litten, sensitivity to error accumulation. In autoregressive prediction, small errors in early predictions can accumulate and compound over time, leading to significant divergence from the true trajectory for longer prediction horizons. Fixed context window. While GRUs have memory, their ability to capture extremely long-range dependencies can still be limited by the depth and capacity of the network and the fixed code snippet of the input window. This GRU-based model serves as a strong baseline, demonstrating the power of recurrent networks for sequential data. However, its limitations highlight the necessity of incorporating structural information, which will be the focus of subsequent sections on graph-aware models. Visualizing predictions. Visualizing predicted trajectories against true trajectories is essential for understanding model performance beyond numerical loss values. This allows for qualitative assessment of how well the model captures motion dynamics and where it tends to deviate. Code is not spoken. To get code, please see the link in description or bio. This simple code snippet example demonstrates how to plot a single feature, e.g., the x-coordinate of a specific joint, over time for both the true and predicted sequences. For comprehensive pose visualization, you would typically use 3D plotting libraries or animation tools to render the full skeleton. This qualitative assessment provides invaluable insights into the model's strengths and weaknesses, especially in capturing the fluidity and naturalness of human motion. Dynamic graph neural networks. Graph neural networks, GNNs, excel at modeling relationships and dependencies within static graph structures. However, many real-world systems are inherently dynamic, with nodes, edges, and their attributes changing over time. Consider a social network where new friendships form, a traffic network with varying road conditions, or a biological network where gene interactions evolve. To accurately model such systems, we need dynamic graph neural networks, dynamic GNNs. Dynamic GNNs extend the capabilities of traditional GNNs by incorporating a temporal dimension. This allows them to capture not only the spatial relationships within a graph at any given moment, but also how these relationships and node states evolve over time. This field is often referred to as spatiotemporal graph neural networks to emphasize the interplay between spatial structure and temporal dynamics. The necessity for dynamic GNNs arises from the limitations of static models when applied to time-varying data. A static GNN would treat each snapshot of a dynamic graph independently, losing crucial information about the transitions and causality between different time steps. Dynamic GNNs, conversely, are designed to learn these intricate temporal dependencies, making them powerful tools for tasks like predicting future graph states, identifying evolving patterns, or classifying time series graph data. Conceptual approaches to dynamic GNNs. There are several paradigms for building dynamic GNNs, each with its own advantages and suitable for different types of problems. We will explore two primary conceptual approaches, treating the entire sequence as a single, large static graph, and processing individual snapshots to infer underlying dynamics. 1. Combining snapshots into a single large graph. One intuitive approach to handling dynamic graph data is to transform the entire sequence of graph snapshots into a single, comprehensive static graph. This unified representation can then be processed by standard GNN architectures, such as graph attention networks, GATs, representing temporal connections. In this approach, every node from each time step is treated as a distinct node in the combined graph. For instance, if code snippet exists at code snippet at code snippet, and code snippet at code snippet, these become code snippet, and code snippet respectively in the global graph. The key to capturing dynamics lies in establishing two types of edges. 1. Spatial edges. These are the original connections between nodes within a single time step, e.g., an edge between code snippet and code snippet. These represent the static graph structure at each moment. 2. Temporal edges. These connect a node at time code snippet to its counterpart at time code snippet, e.g., an edge from code snippet to code snippet. These edges explicitly encode the temporal evolution, allowing information to flow forward or backward through time. The concept of temporal connections encoded as nodes with temporal edges primarily refers to the latter, connecting the same logical entity across different time steps. This creates a computational path for information about a node state at code snippet to influence its state at code snippet, effectively allowing the GNN to learn temporal dependencies. Each node in this combined graph will have features that might include its original attributes, its specific time step, and potentially an embedding representing its time index. The GNN can then leverage its message passing mechanism to aggregate information across both spatial and temporal dimensions simultaneously, adapting existing GNNs, e.g., GAT. Once the dynamic graph is flattened into this unified static representation, any standard GNN architecture can be applied. A graph attention network, GAT, for example, is particularly well suited because its attention mechanism can learn to assign different importance weights to various types of edges, spatial versus temporal, and neighbors. The GAT's self-attention mechanism allows it to selectively focus on relevant neighbors, whether they are spatial neighbors within the same time step or temporal neighbors from adjacent time steps. This flexibility enables the model to effectively learn complex spatiotemporal patterns. The training strategy typically involves feeding the entire combined graph to the GAT, with a loss function designed to predict future node states, edge existence, or other dynamic properties. Code example: constructing a spatiotemporal graph. Let's illustrate how to conceptually build such a graph using code snippet, a popular library for GNNs. We'll assume a simple scenario with two nodes, code snippet and code snippet, over 3 time steps, code snippet, code snippet, code snippet. First, we define a helper to create node features. Each node will have an initial feature vector and a time embedding. Code is not spoken. To get code, please see the link in description or bio. This initial step code snippet generates a feature vector code snippet for every unique spatiotemporal node, e.g., node 0 at time 0, node 0 at time 1, node 1 at time 0, etc. It also creates a code snippet to easily translate between code snippet tuples and their unique code snippet in our combined graph. Each feature vector is augmented with a simple time embedding to provide temporal context. Next, we define the edges. This involves both spatial edges within a time step and temporal edges between time steps for the same original node. Code is not spoken. To get code, please see the link in description or bio. The code snippet function generates the code snippet tensor. It first adds spatial edges, here assuming a fixed adjacency for simplicity, e.g., node 0 is always connected to node 1 at each moment. Then, it adds temporal edges, connecting each code snippet from timestep code snippet to the same code snippet at timestep code snippet. Bidirectional temporal edges are often useful to allow information to flow both forward and backward in time. Finally, we combine these components into a code snippet object. Code is not spoken. To get code, please see the link in description or bio. This final step constructs the code snippet object, which represents our entire spatiotemporal graph. A GNN model can now take this code snippet object as input and perform message passing across both spatial and temporal connections. The model learns to propagate information not just between connected entities at a single moment, but also how an entity's state evolves over time and influences its future self or other entities. 2. Encoding individual snapshots, e.g., neural relational inference (NRI). An alternative approach to dynamic GNNs focuses on processing individual graph snapshots, often sequentially, to infer and predict underlying dynamics. Instead of flattening the entire sequence into one large graph, these methods typically learn a latent representation of the graph state at each time step and use recurrent mechanisms to model the transitions between these states. Neural relational inference, NRI, is a prominent example of this paradigm. High-level conceptual breakdown of neural relational inference, NRI. NRI is designed to infer the underlying causal interactions between objects, nodes, in a system and predict their future trajectories. It leverages a combination of a variational autoencoder, VAE, and a recurrent neural network, RNN, to achieve this. 1. Encoder, VAE component at each time step. The encoder takes the current node features and their observed interactions, if any, and attempts to infer a latent graph structure or a set of latent relationship types between nodes. This VAE component is crucial because it allows the model to learn a probabilistic distribution over potential interactions, rather than just a fixed graph. It essentially answers the question, what are the hidden relationships that best explain the observed data at this moment? 2. Decoder, RNN component, the inferred latent graph structure, or relational types, from a VAE, along with the current node states, are then fed into an RNN. The RNN's role is to propagate information through time, taking into account the inferred relationships. It learns how the latent relationships and node states evolve from one time step to the next, ultimately predicting the future states, e.g., positions, velocities of the nodes. The RNN essentially answers, given these relationships, how will the system evolve over time? The interaction between the VAE and RNN is key. The VAE provides a dynamic, inferred understanding of the relationships, while the RNN uses this understanding to propagate and predict the temporal evolution. This allows NRI to discover and leverage complex, nonlinear dependencies in dynamic systems, even when the explicit graph structure is unknown or changing. Masking nodes for prediction. In models like NRI, prediction often involves masking or omitting future ground truth data for specific nodes or attributes. For example, to predict the future position of an object, its position at code snippet, etc., would be withheld from the model during inference. The model, having learned the underlying dynamics and relational types, is then tasked with generating these missing future values based on the past sequence of observations. This is different from masking features of future nodes in the combined graph approach. Here, it's about predicting the entire state of a node or relationship that has not yet been observed. Challenges of dynamic GNNs. While powerful, dynamic GNNs come with their own set of challenges. Computational complexity. Processing large spatiotemporal graphs, approach 1, can be computationally expensive due to the sheer number of nodes and edges. Similarly, sequential processing of multiple snapshots, approach 2, with complex models like VAEs and RNNs can also demand significant computational resources. Memory usage, storing the entire combined graph or the sequence of individual snapshots, along with their features and edge information, can quickly consume a lot of memory, especially for long sequences or dense graphs. Non-stationarity. Real-world graph dynamics are often non-stationary, meaning the underlying rules governing changes can themselves evolve over time. This makes it challenging for models to generalize over long periods or to UNS. And dynamic patterns. Data availability and annotation. Collecting rich, high-quality temporal graph data is often difficult. Furthermore, annotating such data with precise timestamps and evolving relationships can be labor-intensive. Practical applications. Beyond pose estimation, dynamic GNNs have a wide range of applications. Evolving social networks, predicting new friendships, community formation, or the spread of information/misinformation over time. Dynamic traffic flow prediction, modeling vehicle movement, congestion patterns, and predicting future traffic conditions on road networks. Biological networks, analyzing changes in protein-protein interaction networks, gene regulatory networks, or brain connectivity patterns in neurological disorders. Financial markets, modeling dependencies between stocks or financial entities and predicting market trends. Cybersecurity, detecting evolving attack patterns or anomalous network behavior. Rationale for representative methods, GAT and NRI. The choice of GAT and NRI as representative methods for dynamic GNNs highlights two fundamental paradigms. GET, as part of the combined graph approach, represents the adaptability of existing GNN architectures. It demonstrates that by cleverly restructuring the data, powerful static GNNs can be leveraged to handle temporal dynamics. Its attention mechanism is particularly useful for learning to weigh different types of connections, spatial versus temporal, and identifying critical interactions in a complex spatiotemporal context. NRI, as a sequential processing approach, represents methods that explicitly model latent dynamics and sequential evolution. It showcases how a generative model, VAE, can infer underlying relational structures, while a sequence model, RNN, can then propagate and predict the future based on these inferred relationships. NRI is powerful for scenarios where the exact interactions are unknown or where predicting future states is paramount. Together, these two approaches provide a comprehensive overview of how researchers and practitioners tackle the challenge of modeling and predicting change in interconnected systems using graph neural networks. Graph Attention Network for dynamic graphs. Dynamic graph problems, where both graph structure and node features evolve over time, present a significant challenge for traditional graph neural networks, GNNs. While recurrent neural networks, RNNs, and their variants like GRUs are adept at sequence modeling, they often struggle to capture complex spatial dependencies inherent in graph data. This section explores a foundational, albeit naive, approach to bridging this gap, transforming a dynamic graph problem into a single, larger static graph that can then be processed by a standard GNN, specifically a Graph Attention Network, GAT. Our focus will be on the problem of human pose estimation and prediction. Imagine tracking the joints of a person's body over time. Each joint can be considered a node in a graph, and the physical connections between joints, e.g., shoulder to elbow, form static edges. Over time, the positions and velocities of these joints change, making it a dynamic graph problem. The goal is to predict future joint positions given a sequence of past observations, representing spatiotemporal data as a single static graph. The core idea behind this naive approach is to unroll the temporal dimension into the spatial dimension. Instead of having a sequence of graphs $G_1, G_2, \dots, G_T$, we construct one large graph $G_T$ that encompasses all time steps. For a graph with $and nodes observed over $T$ time steps, the combined spatiotemporal graph $G_T$ will have $n times $T$ nodes. Each node in $G_T$ represents a specific original node at a specific time step. For example, if we have a node $v at time $10, it becomes a unique node $v_T_J in $G_T$. The edges in $G_T$ are constructed in two main ways. 1. Intra-time step, spatial, edges. These edges connect nodes that existed in the same original graph snapshot. For instance, if node $v and $v were connected at time $10 in the original graph $G_J, then the nodes $v_I, T_J, and $v_K, T_J, are connected in $G_T$. This means the static graph structure is replicated for each time step. 2. Inter-time step, temporal, edges. These edges connect corresponding nodes across adjacent time steps. For example, node $v_I, T_J is connected to node $v_I, T_J plus a $and $G_T$. This allows information to flow along the temporal dimension for each original node. By constructing such a graph, we effectively flatten the time dimension into a single graph structure. A standard GNN, like a GAT, can then process this large static graph, learning both spatial and temporal dependencies through its message passing mechanism. Data pre-processing, normalization utility. Before diving into the custom data set, it's crucial to ensure our input features are well scaled. Neural networks often perform better when input features are normalized, preventing features with larger numerical ranges from dominating the learning process. A common technique is min-max scaling, WHI. CH rescales features to a specific range, typically $0, $1 or $-1, $1. For location and velocity data, this can help stabilize training. Code is not spoken. To get code, please see the link in description or bio. The code snippet function performs a standard min-max normalization. It takes an array and target code snippet, e.g., -1 and 1, and scales all values within the array to fit that range. This is applied to both location and velocity data to bring their values into a consistent scale. Implementing the spatiotemporal pose dataset. To use PyTorch geometric, we need to define a custom code snippet that prepares our pose sequences as code snippet objects. Each code snippet object will represent one spatiotemporal graph. Dataset initialization, code snippet. The code snippet method of our code snippet is responsible for loading the raw data and setting up configuration parameters. This includes the paths to preprocessed number.py files containing joint locations, velocities, and the static intra-timestep edge structure. It also defines key parameters like the sequence length, code snippet, the prediction length, code snippet, and the number of joints and dimensions. Code is not spoken. To get code, please see the link in description or bio. In code snippet, we load the pre-processed code snippet, and code snippet. Code snippet and code snippet define the input and prediction sequence lengths. The code snippet is pre-calculated. This SOR holds the indices of the nodes within the unrolled spatiotemporal graph that correspond to the future time steps, code snippet. These are the nodes whose features we will predict. Item retrieval, code snippet. The code snippet method is where the magic happens. For each requested index, it extracts a sequence of code snippet time steps, normalizes the features, constructs the spatiotemporal code snippet, and prepares the code snippet object for PyTorch geometric. Code is not spoken. To get code, please see the link in description or bio. Understanding spatiotemporal code snippet construction. The code snippet is the most critical part of forming our spatiotemporal graph. It's a code snippet tensor where the first row lists source nodes and the second row lists target nodes. Let's illustrate with a small example. Assume we have 3 nodes, n equals 3, and we are looking at 2 time steps, t equals 2. Original static edges, code snippet, meaning node 0 connects to 1, node 1 connects to 2. The nodes in our spatiotemporal graph will be time 0, node 0, index 0, node 1, index 1, node 2, index 2, time 1, node 0, index 3, node 1, index 4, node 2, index 5. Total nodes, 6. 1. Intra-time step, spatial, edges. For each time step, we take the code snippet and shift their indices by code snippet. Code is not spoken. To get code, please see the link in description or bio. This process effectively creates copies of the original graph structure for each time step, ensuring spatial connectivity is maintained within each snapshot. 2 intertime step, temporal, edge. These connect corresponding nodes across adjacent time steps. Node code snippet at time code snippet connects to node code snippet at time code snippet. Code is not spoken. To get code, please see the link in description or bio. These temporal edges are crucial for propagating information along the time axis. Finally, code snippet and code snippet are concatenated to form the complete code snippet for the code snippet object. Code snippet and code snippet. The code snippet tensor contains the indices of the future nodes within the code snippet, node features, tensor that we want to predict. Since our code snippet tensor is flattened code snippet, these indices correspond to the nodes from code snippet to code snippet. The code snippet tensor holds the ground truth values for these masked nodes. In our case, code snippet is the unnormalized location data for the joints in the code snippet future time steps. It's essential that code snippet is aligned with the code snippet, meaning code snippet should be the ground truth for code snippet. When a model predicts code snippet, it will be compared against code snippet using a loss function. Minimal dataset usage example. To see how code snippet works, We can instantiate it and retrieve sample. Code is not spoken. To get code, please see the link in description or bio. This example shows how a code snippet object is structured and what information it contains. The code snippet tensor holds the combined location and velocity features for all code snippet time steps and code snippet nodes. Code snippet defines the spatiotemporal connectivity. Code snippet stores the ground truth for the code snippet future time steps, and code snippet points to the corresponding nodes in code snippet that code snippet refers to. Designing the Graph Attention Network (GAT) model. With our data prepared, we can now define the GAT model. We'll use PyTorch Geometrics code snippet layer, which is an improved version of the original GAT. Code snippet versus code snippet. The original code snippet computes attention weights as $_ij equals \text attention underscore @math w \math underscore I \math underscore j$. This formulation means that the attention mechanism is static for a given pair of nodes, ij, regardless of the query node. This can limit its expressiveness. Code snippet, introduced in How Attentive Are Graph Attention Networks, addresses this by making the attention mechanism dynamic. It computes attention weights as $_ij equals \text attention underscore @math w underscore 1 \math underscore I plus \math w underscore 2 \math underscore j$. This allows the attention mechanism to be more expressive, as the attention value between nodes code snippet and code snippet can depend on which node is querying. For complex spatiotemporal interactions, this increased expressiveness can be beneficial. It allows the model to differentiate more nuanced relationships between nodes across both SPA, C, and time. GAT model architecture, code snippet class. Our code snippet model will consist of multiple code snippet layers, interleaved with code snippet for normalization and code snippet for regularization, to prevent overfitting. Code is not spoken. To get code, please see the link in description or bio. The code snippet class takes code snippet, e.g., 6 for 3D location plus 3D velocity, code snippet, e.g., 3 for 3D location, code snippet, and code snippet. In the code snippet method, the input node features code snippet and code snippet are passed through the GAT layers. Crucially, after processing all layers, we select only the output features corresponding to the code snippet, i.e., the nodes representing future poses, before passing them through a final linear layer for the prediction. Model training and evaluation. Training a GNN model on a custom dataset follows the standard PyTorch deep learning pipeline, defining an optimizer, a loss function, and iterating through epochs. Code is not spoken. To get code, please see the link in description or bio. The code snippet function encapsulates the training loop. It iterates through epochs, calling code snippet to enable dropout and batch normalization updates. For each batch, it moves the code snippet object to the correct device, performs a forward pass, calculates the mean squared error, MSE, loss between the predictions, code snippet, and the ground truth, code snippet, backpropagates the gradients, and updates the model's weights using the Atom optimizer. A validation loop is also included to monitor performance on unseen data and detect overfitting. Code is not spoken. To get code, please see the link in description or bio. The code snippet function is similar to the validation loop, but runs only once on the dedicated test dataset to provide a final, unbiased performance metric. Code snippet and code snippet are used to ensure the model is in evaluation mode and no gradients are computed, respectively. Analysis of results and limitations of the naive approach. While conceptually straightforward, this flattening approach to dynamic graphs often yields suboptimal results for complex tasks like long-term pose prediction. For instance, in our pose estimation problem, this GAT model achieved only around 55% accuracy, measured as the mean squared error against ground truth relative to a baseline. This contrasts sharply with the performance of RNN-based models or more advanced dynamic GNNs. Why does this naive approach struggle despite using a powerful GNN like GTV2? 1. Loss of explicit temporal inductive bias. RNNs inherently process sequences step by step, maintaining a hidden state that explicitly summarizes past information. This provides a strong inductive bias for sequential data. By contrast, in the flattened spatiotemporal graph, time is just another dimension of connectivity. The GAT treats all nodes, spatial and temporal, uniformly. While temporal edges exist, the model doesn't explicitly learn that information flows sequentially or that future states are causally dependent on past states in a distinct manner. The attention mechanism might learn to prioritize temporal connections, but it's not guaranteed or enforced. 2. Too expressive and overfitting. GATs are highly expressive models, capable of learning complex relationships. When applied to a single, very large spatiotemporal graph, this expressiveness can be a double-edged sword. Without a strong temporal inductive bias, the model might try to learn arbitrary correlations across the entire graph, potentially overfitting to specific training sequences rather than generalizing to the underlying temporal dynamics. The model might become too expressive in the sense that it has too much flexibility to connect any node to any other node without adequately prioritizing the sequential nature of the temporal connections. 3. Scalability challenges. For very long sequences or graphs with many nodes, the size of the combined spatiotemporal graph, $n\times T$ nodes, can become enormous. This leads to increased memory consumption and computational cost, making it difficult to scale to real-world applications with continuous, long-running dynamic processes. 4. Lack of directed temporal flow. While we add temporal edges, they are typically undirected in standard GNNs. This means information can flow backward in time, which contradicts the causal nature of many dynamic processes. Future depends on past, not vice versa. While GT's attention can learn directionality, it's not an explicit structural property of the graph. When might this naive approach work? Despite its limitations, this approach isn't entirely without merit. It might perform reasonably well in specific scenarios. Very short time sequences. If code snippet and code snippet are very small, the spatiotemporal graph is less complex, and a GAT might effectively learn the limited temporal dependencies. Highly correlated temporal changes. If the changes between time steps are very subtle and highly predictable from the immediate past, the model might not require complex temporal reasoning. Static graph with evolving node features. If the graph structure is truly static and only node features change, this approach is essentially applying a GNN to a sequence of features, which can be effective. However, for forecasting complex, long-range temporal dependencies in dynamic graphs, this approach demonstrates the need for more sophisticated architectures that explicitly incorporate or learn temporal dynamics. This realization serves as a crucial stepping stone, highlighting why researchers have developed dedicated dynamic graph neural networks that can better emphasize and model the inherent temporal properties of evolving graphs. The next sections will delve into these more advanced methods. Neural relational inference. Neural relational inference, NRI, represents a significant advancement in modeling dynamic systems where both temporal dependencies and underlying relational structures are crucial. It addresses the limitations of simpler models, such as RNNs that capture temporal dynamics but ignore interentity relationships, and naive GNNs that struggle with the evolving nature of connections in dynamic graphs. NRI offers a unified autoencoder-based framework that learns latent graph structures and predicts future states of interacting entities. At its core, NRI is designed to infer the relationships between entities from their observed trajectories and then use these inferred relationships to predict their future movements. This is particularly powerful in scenarios where the connections are not explicitly known or are too complex to define manually, such as in multi-particle systems, human pose estimation, or dynamic social networks. The NRI autoencoder architecture. NRI employs an autoencoder architecture, which consists of two main components, an encoder and a decoder. 1. Encoder. The encoder's primary role is to infer the latent relational graph from the observed time series data of the entities. Given the trajectories of multiple interacting objects, the encoder learns a probability distribution over possible edge types, e.g., attraction, repulsion, no interaction, for each pair of entities. This inferred graph represents the underlying connectivity that explains the observed interactions. 2. Decoder. The decoder takes the original input trajectories, or a portion of them, and the inferred latent graph, specifically the sampled edge types, to predict the future states or trajectories of the entities. It uses the relational information encoded in the graph to propagate messages between entities, allowing it to model complex, interdependent dynamics. This autoencoder structure allows NRI to learn a compact, interpretable representation of the relationships between entities, which can then be used for prediction, anomaly detection, or understanding the underlying physics of system. Learning latent graph structures. The role of Gumbel softmax. A key challenge in learning latent graph structures is that graph edges are typically discrete, e.g., an edge either exists or it doesn't, or it's of a specific type. Directly optimizing over discrete variables is non-differentiable, making it incompatible with standard gradient-based optimization methods used in deep learning. NRI overcomes this using the Gumbel softmax trick. The encoder outputs logits for each possible edge type between every pair of nodes. These logits represent unnormalized log probabilities. To make these discrete choices differentiable, the Gumbel softmax function is applied. The Gumbel softmax distribution is a continuous, differentiable approximation of a categorical distribution. It allows for sampling from a discrete distribution in a way that gradients can still be backpropagated through the sampling process. The code snippet temperature parameter in Gumbel softmax controls the softness of the approximation. As code snippet approaches 0, the Gumbel softmax output approaches a one-hot vector, hard assignment to a single category. As code snippet approaches infinity, the output approaches a uniform distribution over categories. During training, a higher code snippet is typically used to allow for exploration of different edge types, and it is gradually annealed, reduced, to encourage more discrete, definitive assignments as training progresses. During inference, code snippet can be used to obtain actual one-hot vectors, representing a concrete, sampled graph structure. The NRI loss function, a VAE perspective. NRI is formulated as a variational autoencoder, VAE. This means its training objective consists of two main components. 1. Reconstruction loss, negative log likelihood. This term measures how well the decoder reconstructs the observed data or predicts future states, given the inferred latent graph. For continuous data like trajectories, mean squared error, MSE, is commonly used. It encourages the model to generate outputs that are close to the ground truth. The term code snippet in the code snippet calculation arises from the assumption that the reconstruction error follows a Gaussian distribution with a certain variance, code snippet. This effectively scales the MSE loss based on the assumed N. Was level in the data. 2. KL divergence. Regularization. This term measures the difference between the learned posterior distribution of a latent graph, inferred by the encoder, and a predefined prior distribution, e.g., a uniform distribution over edge types. This regularization encourages the latent space to be well-behaved and prevents the encoder from collapsing to a trivial solution. It forces the model to learn meaningful, disentangled representations of the relationships. The total loss is a weighted sum of these two components. Code snippet, where code snippet is a hyperparameter controlling the strength of the KL divergence term. Core components in PyTorch. Let's look at the foundational PyTorch implementation of the code snippet class, which orchestrates the encoder, decoder, and loss calculation. 1. The code snippet class. The code snippet class sets up the overall structure, including hyperparameters and the initial prior distribution for edge types. It acts as a blueprint for the NRI model, requiring separate code snippet and code snippet modules to be passed during instantiation. Code is not spoken. To get code, please see the link in description or bio. This initial block sets up the basic parameters and defines the code snippet method. The code snippet is a crucial component for the KL divergence calculation, representing our baseline assumption about the relationships before observing any data. By default, it's a uniform distribution, implying no PR. Higher preference for any specific edge type. 2. The encoder network code snippet. The encoder's task is to take the input trajectories and output logits for the edge types. A common choice for the NRI encoder is a multi-layer perceptron, MLP, because it can process concatenated node features for pairs of nodes to infer their relationship. Code is not spoken. To get code, please see the link in description or bio. The code snippet takes time series data for all nodes, constructs pairs of nodes, concatenates their features, often averaged or pooled over the time dimension to get a fixed size representation for the MLP, and then feeds these concatenated features through an MLP to predict logits for each edge type. The output code snippet are used by the Gumbel softmax function to obtain differentiable edge probabilities. 3. The decoder network code snippet. The decoder's role is to use the inferred edge types to predict future states. It typically employs an RNN, like GRU, for temporal modeling and message passing to incorporate relational information. Code is not spoken. To get code, please see the link in description or bio. The code snippet is more complex due to its dual role, temporal processing via GRU and relational message passing. It contains a code snippet module for each node's temporal evolution and a code snippet of MLP's code snippet for each edge type to compute messages. The messages are then aggregated based on the inferred code snippet and fed back into the GRU or a final output MLP to predict the next state. The code snippet loop enables multi-step forecasting by iteratively feeding the last predicted state back as input. 4. Calculating the NRI loss. The code snippet method within the code snippet class combines the reconstruction loss and KL divergence. Code is not spoken. To get code, please see the link in description or bio. The code snippet method is central to training. It performs the forward pass through the encoder and decoder, applies Gumbel softmax for differentiable sampling of edge types, and then computes both the reconstruction, MSE, and KL divergence losses. The code snippet flag is crucial for controlling the code snippet parameter of Gumbel softmax, allowing for soft sampling during training and hard sampling during inference. 5. Predicting the future. After training, the NRI model can be used to predict future states. This involves passing the observed historical data through the encoder to infer the latent graph, and then using this inferred graph with the decoder to recursively predict future time steps. Code is not spoken. To get code, please see the link in description or bio. The code snippet method demonstrates the inference process. It first uses the encoder to infer the most likely discrete relationships, using code snippet for concrete sampling, and then leverages the decoder to unroll predictions over multiple future time steps, feeding its own output back as input for the next step. This allows the model to forecast trajectories while respecting the learned relational structure, instantiating and training the NRI model. To put all together, here's how you would instantiate in a simplified training loop for the NRI model. Code is not spoken. To get code, please see the link in description or bio. This example illustrates the instantiation of the encoder, decoder, and the code snippet model, followed by a conceptual training loop. Key aspects include moving the model and data to the correct device, CPU/GPU, zeroing gradients, performing the forward pass to calculate loss, backpropagating, and updating parameters. During inference, the code snippet mode and code snippet context manager are used to disable dropout/batch normalization effects and gradient computation for efficiency. Practical applications and generalization. NRI's ability to infer latent relationships makes it highly versatile. Beyond the common example of human pose estimation and predicting trajectories of interacting particles, it can be applied to dynamic social networks, inferring evolving friendships or professional connections from user activity. Traffic flow prediction, modeling interactions between vehicles or traffic segments to forecast congestion. Financial market analysis, detecting hidden dependencies between stocks or assets based on their price movements. Biological systems, understanding interactions between cells or proteins from time series observations. A significa, NT advantage of NRI is its potential for out-of-distribution OD generalization. By learning the rules of interaction, the edge types, rather than just memorizing trajectories, NRI can generalize to new scenarios or systems with different initial conditions, as long as the underlying interaction mechanisms remain similar. This is a powerful capability for scientific discovery and robust predictive modeling. Further considerations. Hyperparameter tuning. The code snippet, temperature, code snippet, and the code snippet weight for KL divergence are critical hyperparameters that require careful tuning. Code snippet is often annealed during training. Edge embeddings. While the code directly uses code snippet, probabilities, or one-hot vectors. In more complex NRI variants, these discrete edge types might be mapped to continuous edge embeddings, which then modulate message passing in the decoder, offering richer relational representations. Message passing details. The message passing within the code snippet is a simplified example. Real-world GNN message passing functions can be more sophisticated, involving aggregation functions, sum, mean, max, and attention mechanisms. Concrete distribution. The term concrete distribution in NRI schematics refers to the continuous distribution that the Gumbel softmax function produces, which is a relaxation of the discrete categorical distribution. This soft distribution allows for differentiable training. The encoder component within a neural relational inference, NRI, model plays a pivotal role in uncovering the underlying relational structure of dynamic systems. Unlike traditional approaches that either assume a fixed graph or learn node-level embeddings, the NRI encoder is specifically designed to infer the existence and properties of edges, relationships, between entities, nodes, from their observed spatiotemporal features. This section delves into the detailed architecture and implementation of such an encoder, focusing on its custom message passing mechanisms in PyTorch. The encoder's primary function is to transform raw input data, such as a sequence of joint positions and velocities in pose estimation, into a low-dimensional latent representation of edge data. This latent representation, typically in the form of logits, then informs the subsequent variational autoencoder, VE, components of the NRI model, guiding the inference of the most probable graph structure. Base encoder, foundation for custom message passing. The code snippet class serves as an abstract blueprint, providing the fundamental graph utilities and abstract message passing operations required for the NRI encoder. It establishes the initial assumption of a fully connected graph, where every node is potentially connected to every other node, and defines the mechanisms for transforming features between nodes and edges. Initializing the base graph structure. The code snippet method of code snippet sets up the foundational adjacency information for a fully connected graph. This includes defining which nodes send messages, code snippet, and which nodes receive messages, code snippet, for every potential edge. Crucially, self-loops, a node sending a message to itself, are explicitly excluded as they are not typically relevant for inferring relationships between distinct entities. Code is not spoken. To get code, please see the link in description or bio. The code snippet and code snippet tensors are crucial. They define the source and destination nodes for every potential edge in our fully connected graph, excluding self-loops. For code snippet nodes, there are code snippet such directed edges. The code snippet for edge aggregation. A unique aspect of this encoder is the manual implementation of message passing, particularly the code snippet operation. This operation requires aggregating features from multiple incoming edges back to a single node. To facilitate this, a fixed, non-trainable matrix called code snippet is pre-computed. Code is not spoken. To get code, please see the link in description or bio. The code snippet is a code snippet but with code snippet. This design choice means it is part of the model's state, saved and loaded with the model, but its values are fixed and not updated during backpropagation. It acts as a static adjacency matrix, where each row corresponds to an edge and each column to a node, with a code snippet indicating that the edge is incoming T. That node. Transposing code snippet aligns the dimensions correctly for matrix multiplication, allowing us to efficiently sum features from all incoming edges for each node. Message passing utilities, code snippet and code snippet. These methods define how features are transformed between node-centric and edge-centric representations. They are the core of the custom message passing mechanism. Code snippet, transforming node features to edge features. The code snippet function takes node features and creates edge features by concatenating the features of the sender and receiver nodes for each potential edge. Code is not spoken. To get code, please see the link in description or bio. Mathematically, if $h represents the feature vector of node $i, and an edge $e_ij connects node $i sender to node $j receiver, then the feature vector for edge $e_ij is formed by concatenating $h and $f_e_ij equals h_j. This operation is performed efficiently across all batches and all potential edges using tensor indexing. Code snippet, aggregating edge features to node features. The code snippet function performs the reverse operation. It aggregates features from all incoming edges for a given node to produce a new node feature. This is achieved through matrix multiplication with the pre-computed code snippet and subsequent normalization. Code is not spoken. To get code, please see the link in description or bio. Mathematically, for a node $j, its new phi2. Re$ is a sum of features from all edges $e_ij, where $j is the receiver. $j equals \sum underscore I \nec j $. This sum is then normalized by code snippet, which is the constant number of incoming edges for any node in a fully connected graph without self-loops. This normalization helps prevent the aggregated features from growing excessively large with increasing node count, stabilizing training. Illustrative example, code snippet utilities. To better understand how code snippet, and code snippet are constructed, let's consider a small example with code snippet. Code is not spoken. To get code, please see the link in description or bio. This output clearly shows how code snippet and code snippet list the source and destination for each of the code snippet edges, and how code snippet is structured to enable efficient aggregation of edge features back to their respective receiver nodes. RefMLP encoder, concrete implementation with multi-layer perceptrons. The code snippet is a concrete implementation that inherits from code snippet. It utilizes multi-layer perceptrons, MLPs, to transform features at various stages of the message passing process. This allows the model to learn complex, nonlinear mappings for both node and edge representations. Helper module, code snippet. The code snippet is a simple, reusable MLP module used as a building block within a code snippet. It consists of a linear layer, an exponential linear unit, YLU, activation, batch in, normalization, and dropout. Code is not spoken. To get code, please see the link in description or bio. This code snippet module encapsulates common neural network operations, promoting modularity and readability in the code snippet. The conditional batch normalization and dropout allow for flexible configuration. Initializing encoder weights. Proper weight initialization is crucial for stable and efficient neural network training. The code snippet includes a utility method code snippet to apply Xavier normal initialization to its linear layers and set biases to a small positive constant. Code is not spoken. To get code, please see the link in description or bio. Xavier normal initialization aims to keep the variance of activations consistent across layers, preventing vanishing or exploding gradients. Setting biases to a small positive value, e.g., 0.1, can help prevent dead neurons, especially when using ReLU-like activations. Architecting the encoder's forward pass. The code snippet method of code snippet defines the computational graph, orchestrating the sequence of MLP applications and custom message passing steps. This multi-stage process allows the encoder to progressively refine node and edge representations, capturing increasingly complex relational information. The process involves 4 code snippet modules, code snippet through code snippet, and 2 full rounds of code snippet and code snippet message passing. This sequence enables the model to process initial node features, transform them into edge features, aggregate edge features back to nodes, and then repeat the cycle for further refinement. Code is not spoken. To get code, please see the link in description or bio. The flow within the code snippet pass is as follows. 1. Initial node feature processing, code snippet raw spatiotemporal input, flattened across time and feature mentions, is passed through code snippet to generate initial node embeddings. 2. Node-to-edge transformation. Code snippet, these node embeddings are then transformed into edge features by concatenating sender and receiver node embeddings for all potential edges. 3. Edge feature processing. Code snippet, the newly formed edge features are processed by code snippet to learn more abstract edge representations. 4. Edge-to-node aggregation. Code snippet, the processed edge features are aggregated back to their respective receiver nodes, enriching node representations with information from their incoming connections. 5. Refined node feature processing. Code snippet, the aggregated node features undergo further transformation via code snippet. This step allows nodes to integrate information from their local neighborhood. 6. Second node-to-edge transformation. Code snippet, the refined node features are again transformed into edge features. This second round of node-to-edge transformation allows the model to capture higher-order interactions, as the node features now contain information aggregated from their neighbors. 7. Final edge feature processing. Code snippet, these second-round edge features are processed by code snippet. 8. Output logits. Code snippet finally. Code snippet maps the refined edge features to the desired output dimension, typically producing logits that represent the likelihood or properties of each edge. This sequence of operations allows the encoder to progressively refine its understanding of both node and edge relationships, moving from initial observations to a sophisticated latent representation of the graph structure. Each MLP acts as a learnable function that extracts meaningful patterns at its respective stage, while the message passing steps facilitate the flow of information across the graph. Manual message passing versus GNN libraries, a trade-off analysis. The implementation of message passing in the code snippet uses plain PyTorch tensor operations rather than relying on specialized graph neural network, GNN, libraries like PyTorch Geometric, PYG, or Deep Graph Library, DGL. This choice presents both advantages and disadvantages. Advantages of manual implementation: transparency and control. Implementing message passing manually provides a deep understanding of the underlying mechanics. Every tensor operation and data transformation is explicit, which is invaluable for learning and for developing highly customized GNN architectures. Flexibility for novel architectures, for cutting-edge research or highly non-standard message pass. ING schemes, like the specific sender/receiver logic in NRI that might not map directly to standard PYG code snippet operators. Manual implementation offers unparalleled flexibility. Debugging. While initially complex, debugging custom tensor operations can sometimes be more straightforward as you have direct access to every intermediate tensor, unlike the more opaque black box operations in some library abstractions. Disadvantages of manual implementation: complexity and verbosity. As seen, manual implementation involves intricate tensor reshaping, indexing, and concatenation, which can be verbose, error-prone, and harder to read compared to concise library calls. Performance optimization. GNN libraries are often highly optimized for common graph operations, leveraging sparse matrix multiplications, specialized CUDA kernels, and efficient memory management. Manual implementations might not achieve the same level of performance without significant effort. Development time. Developing and debugging custom message passing logic from scratch is significantly more time-consuming than utilizing pre-built, tested, and optimized components from a library. Scalability. Libraries often provide built-in solutions for scaling to large graphs, e.g., mini-batching graph samples, neighbor sampling, which are challenging to implement manually. For the NRI encoder, the choice to implement message passing manually emphasizes educational clarity and the ability to precisely define the unique relational inference process. It ensures that the reader grasps the full mechanics of how information flows and aggregates within the model, without abstracting away critical details. However, for most standard GNN applications, leveraging libraries like PyTorch Geometric is generally recommended for efficiency and ease of development. Practical implications and applications. The code snippet's output, a tensor of latent edge logits, is the inferred representation of relationships between entities. This output is then passed to the decoder component of the NRI model, which typically samples a concrete graph structure based on these logits and uses it to predict future states or properties of the system. In the context of pose estimation and trajectory prediction, the encoder takes the raw joint positions and velocities over time from multiple human body joints, nodes. It then learns to infer the underlying kinematic chain or even dynamic interactions between joints, edges. The output logits represent the likelihood of different types of connections, e.g., bone, muscle, no connection, or simply the strength of a relationship between two joints. This inferred relational graph is then used by the decoder to predict how the pose will evolve over time, demonstrating the power of learning explicit relational structures. Beyond pose data, this encoder architecture is broadly applicable to any spatiotemporal data modeling problem where explicit relationships between entities are crucial but unobserved. This includes physics simulation, inferring interactions between particles or objects from their trajectories; traffic flow prediction, learning relationships between vehicles or road segments; social network analysis, discovering latent connections between users based on their activities; biological systems, modeling interactions between proteins or cells. By transforming raw observational data into a structured, relational representation, the NRI encoder provides a powerful mechanism for understanding and predicting complex system dynamics. Decoding pose data using a GRU. The Neural Relational Inference, NRI, model's decoder plays a pivotal role in predicting the future states of a dynamic system, leveraging the latent relational information inferred by the encoder. Specifically, for spatiotemporal pose data, the decoder takes the current or historical pose information and the sampled underlying relational graph from the encoder to forecast subsequent poses. This section delves into the intricate details of implementing this GRU-based decoder, highlighting how recurrent neural networks are synergistically combined with graph-based message passing to model temporal evolution on a graph. The decoder's primary objective is to generate a sequence of future node features, e.g., joint coordinates for pose data, given an initial state and the inferred graph structure. This is achieved through a recurrent process where, at each time step, the model updates its internal hidden state by incorporating both the previous hidden state and aggregated messages from its neighbors on the graph. The code snippet module, orchestrating prediction. The code snippet class serves as the main architectural component of our decoder. It encapsulates the various linear layers, the custom GRU cell, and the logic for managing graph connectivity and multi-step prediction. Initialization of code snippet. The constructor code snippet sets up all necessary components, including the input and output layers, the core code SNI, pet cell, and precomputes parameters for efficient message passing. Code is not spoken. To get code, please see the link in description or bio. Explanation of code snippet. Code snippet. This is the dimensionality of the input features for each node at a given time step. For pose data, this might be 4 X, Y, VX, VY, or 2XY. Code snippet. This represents the dimensionality of the hidden state maintained by the GRU for each node. It's often the same as code snippet or a multiple thereof, allowing the GRU to learn complex temporal patterns. Code snippet. The dimension of the one-hot encoding for edge types. If you have code snippet edge types, this would be code snippet. Code snippet. The total number of entities, e.g. body joints, in your graph. Code snippet. The total number of distinct relationship types that can exist between nodes. In many NRI implementations, code snippet signifies no edge and an edge exists. Code snippet. If code snippet and code snippet, this effectively means that only one active edge type, the second one, will contribute to message passing. The first edge type is typically reserved for no edge and is often skipped to avoid unnecessary computations or noise. This implies that if the encoder predicts the first edge type, no message is passed. Code snippet. This is the hidden dimension used by the linear layers, code snippet, that process messages before they are aggregated and fed into the GRU. Code snippet, the diamonds. Ionality of the output prediction for each node at each time step. For pose data, this would typically match code snippet. Code snippet. Dropout probability for regularization, helping prevent overfitting. Code snippet and code snippet. These are code snippet instances, each containing code snippet linear layers. Purpose. These layers are crucial for transforming the concatenated sender and receiver hidden states into meaningful messages before they are aggregated. Each edge type gets its own dedicated pair of MLPs, code snippet and code snippet, allowing the network to learn type-specific message transformations. Input dimension clarification. The input dimension for code snippet is code snippet. This is because a message is formed by concatenating the sender's hidden state and the receiver's hidden state, both of which have code snippet dimensions. So, code snippet, dim code snippet, plus code snippet, dim code snippet, equals code snippet. The output of code snippet then becomes the actual message passed along that edge. Next, we define the code snippet and the output layers, along with the pre-computation of graph connectivity. Code is not spoken. To get code, please see the link in description or bio. Explanation of code snippet continued. Code snippet. This is an instance of our specialized code snippet cell. Unlike a standard GRU, this cell is designed to accept an additional input, the aggregated messages from a graph. This is the core mechanism by which the decode leverages the relational information. Output layers, code snippet, code snippet, code snippet. These are standard fully connected layers that transform the final hidden state of the GRU, which is code snippet dimensions, into the predicted output features, code snippet dimensions. A ReLU activation is typically applied between code snippet and dropout for regularization. Graph connectivity, code snippet, code snippet. These tensors define the graph structure for message passing. Code snippet stores the indices of receiver nodes, and code snippet stores the indices of sender nodes for all possible directed edges in the graph. For a graph with code snippet nodes, there are code snippet possible directed edges, excluding self-loops. These are pre-computed to avoid recalculating them at every forward pass, improving efficiency. Code snippet. This is a crucial pre-computed matrix that facilitates the aggregation of messages from edges to nodes. Purpose. After messages are computed for each edge, they need to be summed up for each receiving node. This sparse matrix, often called an adjacency matrix for message aggregation, allows for efficient matrix multiplication to achieve this sum. Construction. For each node code snippet, the row code snippet of code snippet will have ones at the columns corresponding to all edges where node code snippet is the receiver. When multiplied by a vector of edge messages, this effectively sums up all incoming messages. For each node, isolated example, code snippet construction and usage. To illustrate how code snippet works, consider a simple graph with 3 nodes. Code is not spoken. To get code, please see the link in description or bio. This example clearly shows how code snippet transforms edge-level messages into node-level aggregated messages, which are then passed to the GRU. The code snippet network, graph-informed recurrence. The heart of the decoder's temporal modeling is the code snippet cell. Unlike a standard GRU, this custom implementation is designed to explicitly incorporate the aggregated messages from the graph structure into its gating mechanisms, allowing the hidden state updates to be informed by relational context. Code snippet initialization and forward pass. Code is not spoken. To get code, please see the link in description or bio. Explanation of code snippet. Role of code snippet. The standard GRU takes only the current input and the previous hidden state. Our code snippet extends this by also taking code snippet, aggregated messages from the graph, as an input. This allows the GRU to update its hidden state not just based on a node's own temporal evolution, but also on the information flowing from its neighbors as determined by the sampled graph. Input dimensions. Code snippet. The dimension of the node's individual features at the current time step. Code snippet. The dimension of the GRU's hidden state. Code snippet. The dimension of the aggregated messages received by each node. This is the output dimension of code snippet layers, which is code snippet. Code snippet. This is code snippet. This concatenation, code snippet, is the key modification. Instead of feeding only the raw code snippet to the input to hidden linear layers, e.g., code snippet, code snippet, code snippet, we feed a combination of the current node features and the aggregated graph messages. This means the GRU's gates, reset, update, new, directly consider both the node's own data and its contextual graph information when deciding how to update the hidden state. Gate computations. The core GRU equations remain the same, but the code snippet linear transformations now operate on code snippet. Reset gate. Code snippet controls how much of the previous hidden state to forget. Update gate. Code snippet controls how much of the previous hidden state to keep and how much of the new candidate hidden state to add. New gate. Code snippet computes a candidate hidden state based on the current input and the reset gated previous hidden state. Hidden state update. The final hidden state is a linear interpolation between the previous hidden state and the new candidate hidden state, controlled by the update gate. Simplified, standalone code snippet example. To further illustrate the code snippet's operation, let's look at a minimal example with dummy tensors. Code is not spoken. To get code, please see the link in description or bio. This example confirms the code snippet correctly processes the three inputs, code snippet, code snippet, code snippet, and outputs the updated hidden state with the expected shape. Single-step prediction, code snippet. The code snippet method within code snippet encapsulates the logic for performing one recurrent step of the decoder. This involves extracting messages, processing them based on edge types, aggregating them at the nodes, feeding them into the code snippet, and finally producing a prediction for the current time step. Code is not spoken. To get code, please see the link in description or bio. Explanation of code snippet. Part 1. Message aggregation. Message extraction. Code snippet and code snippet are created by indexing the global code snippet state tensor using code snippet and code snippet. This efficiently gathers the hidden states of all sender and receiver nodes for every possible edge. Concatenation. Code snippet is formed by concatenating code snippet and code snippet. This combined representation forms the raw input for the edge-specific message processing MLPs. Message processing MLPs. Code snippet and code snippet are code snippets, meaning they contain multiple linear layers, one for each edge type. The loop code snippet iterates through these edge type specific MLPs. Code snippet handles code snippet. If code snippet, it starts from index 1, effectively ignoring the first edge type, e.g., no edge. This means only messages corresponding to active or EXI. Sting relationships are processed. Code snippet. This is where the sampled edge probabilities from the encoder are crucial. Code snippet has shape code snippet. By slicing code snippet, we extract the probabilities for the ith edge type for all edges. This code snippet tensor then acts as a weighting factor. If code snippet indicates a strong probability, close to 1, for this code snippet th edge type for a particular edge, then code snippet, the process message, is fully included in code snippet. If the probability is low, close to 0, that message is largely ignored. This effectively selects or weights the messages based on the inferred relationship type from the encoder, making the decoder's message passing dynamic and relational. Normalization factor, code snippet. This factor is used to average the contributions from the active edge types. If code snippet is code snippet and code snippet is 2, then code snippet will be 1, meaning no averaging is performed as only one active edge type is considered. If multiple active edge types contribute, this normalizes their combined influence. Edge-to-node aggregation, code snippet. This is the final step of message aggregation. The code snippet, which are edge-level messages, weighted by code snippet, are multiplied by the transpose of code snippet. As explained earlier, this matrix multiplication efficiently sums up all incoming messages for each node, resulting in code snippet, which are node-level aggregated messages. Now, we feed these aggregated messages and the current node features into the code snippet and generate the prediction. Code is not spoken. To get code, please see the link in description or bio. Explanation of code snippet, Part 2, GRU update and prediction. GRU update, code snippet. The current node features code snippet, the previous hidden state, code snippet, and the newly aggregated messages, code snippet, are passed to the code snippet to compute the updated hidden state for each node. This is where the core temporal and relational modeling happens. Output prediction. The code snippet state is then passed through a series of linear layers, code snippet, code snippet, code snippet, with ReLU activations and dropout to transform it into the final predicted node features, code snippet. This code snippet represents the model's estimate for the next state of each node, e.g., the next x, y, vx, vy coordinates. Residual connection, code snippet. This is a common practice in deep learning, especially for sequence modeling. Instead of predicting the absolute next state, the model predicts the change or residual from the current input state. Justification. 1. Easier learning. It's often easier for a neural network to learn small changes, residuals, than to learn the entire complex output from scratch, especially if the current state provides a good baseline. 2. Stability. It can improve training stability and allow for deeper networks. 3. Identity. Mapping. If the model determines that no change is needed, it can simply output zeros for the residual, effectively preserving the input. In the context of pose data, this means the model is learning to predict the displacement of joints rather than their absolute positions, which can be a more stable and efficient learning task. Multi-step prediction, the main code snippet pass. The main code snippet method of code snippet orchestrates the entire multi-step prediction process, managing the recurrent loop and implementing techniques like teacher forcing. Code is not spoken. To get code, please see the link in description or bio. Explanation of code snippet. Input code snippet. If code snippet is code snippet is expected to be the entire ground truth sequence of node features code snippet. If code snippet is code snippet, e.g., during inference, code snippet is typically just the initial state code snippet. Code snippet initialization. If no initial hidden state is provided, it's initialized to zeros. Code snippet list. This list accumulates the code snippet predictions from each code snippet call. Prediction loop. The code snippet loop drives the recurrent prediction. Teacher forcing. This is a critical training technique for recurrent neural networks. Concept. During training, instead of feeding the model's own prediction from the previous time step as input for the current time step, which can accumulate errors, teacher forcing sometimes feeds the ground truth value for the current time step. This helps the model learn faster and more stably, especially in the early stages of training, by providing it with correct historical context. Implementation. Code snippet. A random coin flip decides whether to apply teacher forcing for the current step. Code snippet controls how often this happens. Code snippet. If teacher forcing is applied, the ground truth data for the current code snippet is used as input. Code snippet. If teacher forcing is not applied, or for the first step if code snippet is code snippet, the model's own code snippet diction from the previous step is used as input for the current step. This mimics the inference scenario. Trade-offs. While beneficial for training, pure teacher forcing can lead to a discrepancy between training and inference because during inference, the model always uses its own previous predictions. A decaying code snippet over training epochs is often used to mitigate this. Code snippet. After the loop, all individual time-step predictions are stacked into a single tensor, forming the complete predicted trajectory. This detailed breakdown of the code snippet and code snippet provides a comprehensive understanding of how the neural relational inference model decodes latent graph representations to predict future spatiotemporal trajectories, illustrating the powerful synergy between recurrent neural networks and graph message passing. This architecture has broad applications from predict ing human motion in robotics and animation to forecasting molecular dynamics or traffic flow on complex networks. Training the NRI model. Training the Neural Relational Inference (NRI) model is the culmination of integrating its sophisticated encoder and decoder components to learn underlying dynamics and predict future states. This process involves a carefully constructed training loop, a multi-component loss function, and robust evaluation strategies to assess the model's performance on spatiotemporal trajectory prediction tasks like human pose estimation. The deep learning training loop for NRI. The core of training any deep learning model is the iterative process of feeding data, calculating loss, adjusting parameters, and evaluating performance. For the NRI model, this loop needs to account for its variational autoencoder, V, nature, and its sequential prediction capabilities. Essential setup, model, optimizer, and data loaders. Before entering the training loop, we must instantiate our model, define the optimizer that will adjust its parameters, and set up data loaders to efficiently feed data in batches. Code is not spoken. To get code, please see the link in description or bio. This initial setup block prepares all necessary components. Code snippet, mocked as code snippet for this example, encapsulates the encoder, e.g. code snippet, and decoder, e.g. code snippet, architectures detailed in previous sections. The code snippet optimizer is a common choice for its efficiency, and code snippet is a crucial learning rate scheduler that helps stabilize training by reducing the learning rate when validation performance stagnates, preventing oscillations around the optimal loss. Code snippet and code snippet, mocked here, are standard PyTorch utilities for efficient data loading and batching. The epoch loop. Training proceeds in epochs, where each epoch represents a full pass over the entire training dataset. Code is not spoken. To get code, please see the link in description or bio. Each epoch begins by setting the model to code snippet mode. This is critical because certain layers, like code snippet or code snippet, behave differently during training, e.g., applying dropout, calculating batch statistics, than during evaluation. We also initialize accumulators for different loss components to monitor their evolution throughout the epoch. Batch processing and forward pass. Inside the epoch loop, we iterate through batches of data. For each batch, we perform a forward pass to calculate the model's output and the associated loss. Code is not spoken. To get code, please see the link in description or bio. The first step within the batch loop is code snippet. This clears any accumulated gradients from previous backward passes, ensuring that gradients are computed only for the current batch. The code snippet function is the heart of the forward pass, computing both the reconstruction loss, negative log likelihood, NLL, and the regularization loss, Kullback-Leibler divergence, KL divergence. The code snippet parameter is a flag that indicates whether the raw outputs, logits, from the Gumbel softmax layer, representing the inferred edge probabilities, should be returned or processed internally. While not explicitly used in this snippet, it's often useful for debugging or further analysis of the inferred graph structure. Understanding the VE loss components. The NRI model, being a V, optimizes a combined loss function, the negative log likelihood, NLL, and the Kullback-Leibler, KL, divergence. Negative log likelihood, NLL, / reconstruction loss. This term measures how well the decoder reconstructs the input data. For continuous data like trajectories, mean squared error, MSE, is commonly used, which is equivalent to NLL under the assumption of Gaussian noise. A lower NLL means the model can accurately predict the observed sequences. Code is not spoken. To get code, please see the link in description or bio.python. Total_loss.backward, compute gradients. Optimizer.step, update model parameters. Code is not spoken. To get code, please see the link in description or bio.python. Validation loop. Model.eval. Set the model to evaluation mode. Total_loss equals 0.0. Total_LL equals 0.0. Total_KL equals 0.0. With torch.no_grad, disable gradient computation for validation. For batch_x, data in enumerate, val_theta_loader. NLL, KL_IV, val_loss equals model.calculate_loss. Data, return_logits equals true. Total_loss plus equals val_loss.item. Total_val plus equals NLL.item. Plus item. Average_train_loss equals total_tra. Inning_loss /len, train_theta_loader. Average_loss equals total_loss /len, val_theta_loader. Average_LL equals total_loss /len, train_theta_loader. Average_LL equals total_LL /len, val_theta_loader. Average_KL equals total_loss /len, train_theta_loader. Average_KL equals total_KL /len, val_theta_loader. Printf epic /epics time. Start time. Point 2 fs. Printf train loss. Average_loss. Point 4 f LL. Average_LL. Point 4 f KL. Average_KL. Point 4 f. Printf val loss. Average_loss. Point 4 f LL. Average_LL. Point 4 f KL. Average_KL. Point 4 f. Learning rate scheduler step. The scheduler monitors the validation loss, average_loss, and adjusts LR. Training_scheduler step, average_loss. Early stopping logic. Using NLL as the primary tuning loss, as it directly reflects reconstruction. The professor mentioned NLL as code snippet for code snippet. If average_LL best_loss. Best_loss equals average_L. Epochs_improve equals 0. Save the best model state. Torch.save model.state_predict best_model.pth. Printf new best validation NLL best_loss. Point 4 f. Model save. Else. Epochs_improve plus equals 1. Printf validation NLL did not improve for epochs_improve epochs. If epochs_improve equals early_stopping_patience. Printf early stopping triggered after early_stopping_patience epochs without improvement. Break. Code is not spoken. To get code, please see the link in description or bio.python. Def evil_forward_prediction model data_loader. Prediction_steps burn_in return_errors equals false. Evaluates the model's ability to predict multiple future time steps. Args. Model. NN. Module the trained NRI model. Data_loader. Torch.utils.data. A data loader for evaluation data. Prediction_steps. Int number of future time steps to predict. Burn_in. int number of initial frames to observe before starting prediction. These frames initialize the model's internal state. Return underscore total underscore errors. Bool, if true, returns accumulated errors for all batches. Otherwise, returns average MSE per frame. Returns float or list. Average MSE per frame over predicted steps or list of errors. Model.eval, set model to evaluation mode. All underscore errors equals to accumulate MSE for each predicted step. With torch.no underscore grad. For batch underscore x, data and enumerate, data underscore loader. Data shape, batch underscore size, sequence underscore length, number underscore atoms, input underscore dims. Slice the input data to get the burn-in sequence. Inputs, shape, batch underscore size, burn underscore, number underscore atoms, input underscore dims. Inputs equals data, colon, burn underscore, targets, shape, batch underscore size, prediction underscore steps, number underscore atoms, input underscore dims. These are the ground truth frames we want to predict. Targets equals data, colon, burn underscore in plus prediction underscore steps. Use the model's predict underscore future method. This method iteratively predicts future frames based on the burn-in sequence. It returns a list of tensors, where each tensor is a predicted frame. Predicted underscore frames. List of batch underscore size, number underscore atoms, input underscore dims, tensors. P. Predicted underscore frames equals model.predict underscore future. Inputs, prediction underscore steps, teacher underscore forcing equals false. Calculate MSE for each predicted step. Batch underscore errors equals. For I in range, prediction underscore steps. Ensure predicted underscore frame and target underscore frame have compatible shapes. For example, if predict underscore future returns B, N, D, but target is B, N, D. Target underscore frame shape, batch underscore size, number underscore atoms, input underscore dims. Target underscore frame equals targets colon I. Predicted underscore frame equals predicted underscore frames I. Reshape if necessary to calculate MSE. For example, if model predicts B and D, but target is B and D, predicted underscore frame equals predicted underscore frame dot view, target underscore frame dot shape. MSE equals F dot S underscore loss, predicted underscore frame, target underscore frame, reduction equals mean. Batch underscore errors that append MSE dot item. All underscore errors that append batch underscore errors. If return underscore total underscore errors. Flatten the list of lists into a single list of errors. Flat underscore errors equals error for sublist and all underscore errors for error in sublist. Return flat underscore errors. Else, calculate average MSE across all batches and all prediction steps. Sum all errors and divide by number of batches prediction underscore steps. Total underscore errors equals sum batch underscore errors, for batch underscore errors and all underscore errors. Total underscore predictions equals len, all underscore errors, prediction underscore steps. Return total underscore errors slash total underscore predictions if total underscore predictions, 0 else 0.0. Example usage of the evaluation function. Average underscore prediction equals eval underscore forward underscore prediction. Model, val underscore in underscore loader, prediction underscore steps, burn underscore in. Print F, average multi-step prediction MS. Average underscore prediction, 0.4 F. Code, snippet burn underscore I. Encode, snippet burn underscore 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 encode, snippet evil underscore forward underscore prediction code, snippet teacher underscore forcing equals false code, snippet teacher underscore forcing equals true code, snippet teacher underscore forcing equals false code. Snippet evil underscore forward underscore prediction code, snippet model, dot predict underscore future code, snippet temp code, snippet prior underscore variance code, snippet encoder underscore hidden code, snippet decoder hidden code, snippet dims code, snippet learning underscore rate code, snippet traducer on plateau code. Snippet factor code, snippet patience code, snippet burn underscore in code, snippet prediction underscore steps, These influence the evaluation setup and should be chosen based on the task requirements and the inherent temporal dependencies in the data. Tuning these parameters often involves a combination of grid search, random search, or more advanced optimization techniques like Bayesian optimization, coupled with careful monitoring of training and validation loss curves. Practical applications beyond pose estimation. While this section focuses on human pose estimation, NRI's ability to infer latent interaction networks makes it broadly applicable to various domains where explicit graph structures are unknown but interactions are crucial. Biological systems. Modeling interactions between proteins, cells, or organs where direct observation of connections is difficult. Financial markets. Inferring relationships between different stocks or assets based on their price movements to predict market trends. Traffic flow predicting. Understanding how vehicles influence each other's movement on a road network to predict congestion. Social network analysis. Discovering hidden communities or influential individuals by inferring interaction patterns from user activity. By understanding the training dynamics, evaluation metrics, and the underlying theoretical motivations, you are now equipped to implement, train, and apply the NRI model to a wide range of complex spatiotemporal problems. Under the hood. Dissecting spatiotemporal GNNs. This section delves into the intricate mechanisms of the core models employed throughout this chapter. Recurrent neural networks, specifically gated recurrent units, graph attention networks, and the neural relational inference model. Understanding their internal workings is crucial for truly grasping how they capture complex spatiotemporal dependencies in dynamic graph problems like pose estimation. 1. Recurrent neural networks, RNNs, and GRUs. Recurrent neural networks, RNNs, are designed to process sequential data, where the output at any step depends not only on the current input, but also on previous inputs. This makes them ideal for modeling temporal dependencies, such as predicting future poses based on a sequence of past poses. The vanishing gradient problem. A fundamental challenge with vanilla RNNs is the vanishing gradient problem. During backpropagation through time, BPT, gradients can shrink exponentially as they propagate backward through many time steps. This makes it difficult for the network to learn long-term dependencies, as the influence of earlier inputs on current outputs becomes negligible. To mitigate this, architectures like long short-term memory, LSTM, networks, and gated recurrent units, GRUs, were developed. They introduce gates that regulate the flow of information, allowing the network to selectively remember or forget past information, thereby preserving gradients over longer sequences. Gated recurrent unit, GRU, architecture. GRUs are a simplified variant of LSTMs, offering a good balance between performance and computational efficiency. A GRU cell processes an input sequence element by element, maintaining a hidden state that encapsulates information from previous time steps. Let's break down the GRU's core components. Update gate, code snippet. This gate controls how much of the previous hidden state, code snippet, should be carried over to the current hidden state, code snippet, and how much of the new candidate hidden state, code snippet, should be incorporated. A value close to 1 means keep the old hidden state, while a value close to 0 means discard the old hidden state and rely more on the new input. Reset gate, code snippet. This gate determines how much of the previous hidden state, code snippet, is relevant for computing the new candidate hidden state, code snippet. A value close to 0 means reset the memory, ignoring the previous hidden state's influence on the candidate. Candidate hidden state, code snippet. This is a potential new hidden state, computed by combining the current input, code snippet, and a selectively reset version of the previous hidden state. Final hidden state, code snippet, the actual hidden state for the current time step, which is a linear interpolation between the previous hidden state and the candidate hidden state, weighted by the update gate. The equations for a GRU cell are $ begin aligned, R_T and equals / sigma W / H plus // Z_T and equals / sigma W / H x50 plus z backslash tilde h underscore t and equals backslash tan w underscore h backslash odit h plus backslash ha pocherkonikte a rovno jeden z pocherkonikte odot ha pocherkonik lava zložená zátvorka jeden pravá zložená zátvorka plus z pocherkonikte odot tilde lava zložená zátvorka ha pravá zložená zátvorka pocherkonikte backslash end aligned $, where $sigma dollar is the sigmoid activation function. $tan$ is the hyperbolic tangent activation function. $W$ and $B$ are learnable weight matrices and bias vectors, and $\oded$ denotes element-wise multiplication. Code example, custom GRU cell. To illustrate these internal mechanics, let's implement a simplified custom GRU cell in PyTorch. This helps demystify the code snippet module by showing the underlying tensor operations. Code is not spoken. To get code, please see the link in description or bio. This initial part of our code snippet defines the necessary linear layers for each gate and prepares the combined input by concatenating the current time steps input code snippet with the previous hidden state code snippet. This combined vector will be fed into the gate computations. Code is not spoken. To get code, please see the link in description or bio. Here, we compute the reset gate, code snippet, and the update gate, code snippet. Both use a linear transformation followed by sigmoid activation. The sigmoid ensures that the gate values are between 0 and 1, acting as selectors or filters for information flow. Code is not spoken. To get code, please see the link in description or bio. This block calculates the candidate hidden state, C. Code snippet. Crucially, the code snippet, reset gate, is applied element-wise to code snippet before concatenation with code snippet. This allows the GRU to selectively forget parts of the previous hidden state when computing the new candidate. The code snippet activation squashes the output of the linear layer to the range, -1. Code is not spoken. To get code, please see the link in description or bio. Finally, the current hidden state code snippet is computed. It's a weighted average between the previous hidden state code snippet and the new candidate code snippet, where the weights are determined by the update gate code snippet. If code snippet is close to 1, the new candidate code snippet contributes more. If code snippet is close to 0, code snippet is largely preserved. This mechanism enables the GRU to control how much new information is incorporated and how much old information is retained. Teacher forcing in sequential models. When training sequential models like RNNs and GRUs, especially for tasks like sequence prediction, a technique called teacher forcing is often used. Instead of feeding the model's own predictions from the previous time step as input to the current time step, teacher forcing feeds the actual ground truth value from the training data. This approach stabilizes training by ensuring that the model always receives correct and high-quality inputs, preventing it from spiraling off into incorrect predictions early in training. However, it can create a discrepancy during inference when ground truth is unavailable and the model must rely on its own predictions, a phenomenon known as exposure bias. Strategies like scheduled sampling, where teacher forcing is gradually phased out during training, can help mitigate this. 2. Graph Attention Networks, GATs. Graph Attention Networks, GATs, are a powerful class of graph neural networks, GNNs, that extend the concept of message passing by allowing nodes to learn the relative importance of their neighbors. This is achieved through a self-attention mechanism, which assigns different weights to different neighbors during the aggregation process. Revisiting graph attention. In traditional GNNs, messages from neighbors are often aggregated uniformly or based on simple degree normalization. GATs introduce an attention mechanism to learn an adaptive weighting. For a node $, its new feature representation is computed by aggregating transformed features from its neighbor's $j backslash in backslash mathcal $, weighted by learned attention coefficients $backslash alpha underscore ij $. The attention mechanism, computing attention coefficients. The attention coefficient $\alpha underscore ij between node $i and its neighbor $j indicates the importance of node $j(s) features to node $i. It's typically computed as follows. 1. Feature transformation. First, the features of node $i, $h_, and node $j, $h_, are transformed by a shared linear projection, e.g., a weight matrix $w$. $math h underscore I equals \math w\math h underscore I quad \math h underscore j equals \math w \math underscore j. 2. Raw attention score. These transformed features are then concatenated and fed into a shared attention mechanism $, which is typically a single-layer feed-forward neural network followed by a leaky-ReLU activation. This produces a raw, unnormalized, attention score $e underscore ij $. E underscore ij equals \text leaky-ReLU \math a caret t \math h underscore I \math h underscore j $, where $math a is a learnable attention vector and $, denotes concatenation. 3. Normalization. The raw attention scores $e underscore ij are then normalized using a softmax function over all neighbors of node $i to ensure they sum to 1. This makes them comparable across different neighbors. Barra inversa alfa trattino basso ij uguale barra inversa frac barra inversa exp e trattino basso ij o barra inversa sum trattino basso k barra inversa in barra inversa matcal oi f barra inversa exp e trattino basso k. Aggregating messages with attention. Once the attention coefficients $\alpha underscore ij are computed, they're used to weight the transformed features of the neighbors. The new feature representation for node $i, denoted $, is then calculated as a weighted sum of its neighbors' transformed features. $math underscore I equals \sigma left sum underscore j and mathcal I alpha j math w math underscore j right. Where $sigma is an activation function, e.g., YLU or ReLU. Multi-head attention. Similar to the transformer architecture, GATs leverage multi-head attention. This involves performing the attention calculation independently $k times with different, independent attention mechanisms, i.e. different $w matrices and attention vectors $math a. The results from these $k heads are then typically concatenated or averaged to produce the final output feature for each node. Multi-head attention allows the model to learn different types of relationships between nodes, enhancing the model's capacity and robustness. For example, one head might focus on structural connectivity, while another focuses on semantic similarity. Code example: custom GAT layer core. Let's look at the core operations within a GAT layer in PyTorch, focusing on how attention coefficients are computed and applied. Code is not spoken. To get code, please see the link in description or bio. This initial part of our code snippet sets up the necessary learnable parameters: code snippet for feature transformation and code snippet for the attention mechanism. In the code snippet pass, node features code snippet are first linearly transformed to code snippet. The helper function code snippet is then called to create pairs of node features for attention calculation. Code is not spoken. To get code, please see the link in description or bio. Here, the raw attention scores code snippet are computed by multiplying the code snippet concatenated features with the attention vector code snippet and applying leaky-ReLU. Crucially, we then mask out the attention scores for non-existent edges using the adjacency matrix code snippet. This ensures that only true neighbors contribute to the attention calculation. Finally, code snippet is applied along code snippet across neighbors to normalize the scores, and dropout is applied for regularization. Code is not spoken. To get code, Please see the link in description or bio. The final part of the code snippet pass performs the aggregation. The normalized attention scores are multiplied by the transformed features code snippet to produce the new node features code snippet, which are then passed through an activation function, e.g., YELU. The code snippet helper function efficiently creates all possible pairs of code snippet vectors for the attention calculation, using broadcasting to avoid explicit loops. GATs for spatiotemporal data, limitations, and considerations. While GATs excel at capturing spatial relationships, their application to dynamic, spatiotemporal problems requires careful consideration. A naive approach might involve 1. Snapshot-based GATs. Applying a GAT to each time slice independently. This ignores temporal dependencies. 2. Augmented node features, appending temporal features, e.g., time step, time since last event, to node features. 3. Stacked GATs with RNNs, using a GAT to capture spatial features at each time step and then feeding these spatially enriched features into an RNN/GRU to model temporal evolution. However, these approaches can be inefficient or fail to capture the complex interplay between spatial and temporal dynamics. For instance, in dynamic graphs, the relationships themselves can change over time. This is where models like neural relational inference, NRI, offer a more sophisticated solution by explicitly inferring and utilizing dynamic relational structures. 3. Neural relational inference, NRI, model. The neural relational inference, NRI, model is designed to learn the underlying interaction graph between entities directly from their observed trajectories. It effectively addresses spatiotemporal problems by simultaneously modeling spatial dependencies, the interaction graph, and temporal dynamics, how entities evolve given their interactions. NRI frames this problem within the context of a variational autoencoder, V. NRI as a variational autoencoder, V. At its core, NRI is a VE. It consists of two main components. Encoder, inference model. This part takes the observed trajectories of all entities as input and infers a probabilistic distribution over the latent interaction graph, a discrete adjacency matrix. This graph represents the relationships between entities. Decoder, generative model. This part takes the inferred latent graph and the initial states of the entities, then predicts their future trajectories. It essentially generates the sequence of states given the inferred relationships. The V framework allows NRI to learn a meaningful latent representation, the graph, by optimizing a loss function that balances reconstruction accuracy, how well the decoder predicts trajectories, with a regularization term, how well they infer. Red latent space conforms to a prior distribution. 3.1. The NRI encoder inference model. The encoder's primary role is to infer the latent graph structure from the input node trajectories. This involves a sophisticated message passing mechanism, inferring latent relations. The encoder processes the input trajectory $x equals $x_1 dots $x_t $fork $entities, where $x_t is the state of all entities at time $t. It aims to infer a latent adjacency matrix $z in euro, current in times in $, that describes the type of relationship between each pair of entities. The process involves two main message passing steps. Code snippet. Messages are sent from individual nodes to potential edges, pairs of nodes. Code snippet. Messages are aggregated from edges back to nodes. These steps are often implemented using multi-layer perceptrons, MLPs, and aggregation functions. Message passing, code snippet. For every potential edge j, between node $i and node $j. The encoder first computes an edge embedding or message that encapsulates information about the interaction between these two nodes. This is typically done by concatenating the features of node $, and node $j, or their time-aggregated representations, and passing them through an MLP. $. M underscore IJ equals backslash text MLP underscore backslash text H underscore J. Dollar, where $H underscore dollar and $H underscore J dollar are the features of node $I dollar and $J dollar derived from their trajectories. In NRI, these features are often the outputs of shared RNN, e.g. GRU, that processes EA. CH node's individual trajectory. Code example, NRI encoder code snippet message function. Let's consider a simplified code snippet message function where we have node features and want to compute edge messages. Code is not spoken. To get code, please see the link in description or bio. This code snippet module takes code snippet, e.g. outputs from a GRU for each node trajectory, and generates messages for all potential edges. It efficiently uses code snippet and code snippet to create pairs of sender and receiver features without explicit loops, which are then concatenated and passed through an MLP. Each code snippet now represents a message from node code snippet to node code snippet, or about the code snippet relationship. Message passing, code snippet. After computing messages for all potential edges, these edge messages are aggregated back to the nodes. For each node $J dollar, the code snippet step aggregates all incoming messages $M underscore AJ dollar from its neighbor's $I dollar, or from all other nodes $I dollar if the graph is dense. This aggregation is typically a sum or mean, followed by another MLP. H underscore J equals backslash text MLP for backslash text, so backslash left, backslash sum underscore I backslash neck, J backslash right. The result, $H underscore J dollar, is a new node level representation that incorporates information from all its connected edges. Code example, NRI encoder code snippet aggregation. Code is not spoken. To get code, please see the link in description or bio. The code snippet module takes the code snippet and sums them up for EAC. H target node. We explicitly mask out self loops, code snippet to code snippet messages before summation, as these typically do not represent a distinct relationship in the same way as internode connections. The aggregated messages are then passed through another MLP to produce the final node-level representations from the encoder. These aggregated node representations are then used to predict the parameters, mean and log variance, of the posterior distribution $Q, ZX, dollar over the latent graph $Z dollar. The Gumbel softmax trick for discrete latent variables. Since the latent graph $Z dollar is a discrete adjacency matrix representing connection types, e.g., no edge, attraction, repulsion, directly sampling from it during backpropagation would be problematic due to the non-differentiable sampling operation. The Gumbel softmax trick, also known as concrete distribution, provides a differentiable approximation to sampling from a categorical distribution. Instead of directly sampling discrete values, the Gumbel softmax trick allows us to sample approximately discrete values that are differentiable with respect to their inputs. It works by adding Gumbel noise to the logits of a categorical distribution and then applying a softmax function with a temperature parameter $\tau dollar. As $tau to $0, the output of the Gumbel softmax becomes a one-hot vector discrete. But for $tau greater than $0, it's a continuous, differentiable approximation. Y počerkovníka rovno frac ľavá zložená zátvorka exp log pi počerkovníka plus g počerkovníka lomka tu pravá zložená zátvorka ľavá zložená zátvorka sum počerkovník. V ligu vienas the log pi plus 8 tau. Where $_k$ are the unnormalized log probabilities, logits, for category $K$. $G_K$ are ID samples from a Gumbel 0, 1 distribution, and $tau is the temperature. Code example, Gumbel softmax implementation. Code is not spoken. To get code, please see the link in description or bio. This code provides a utility for the Gumbel softmax trick. Code snippet generates the necessary random noise. Code snippet combines the logits with this noise and applies the temperature-scaled softmax, yielding a differentiable, soft categorical distribution. The code snippet parameter allows for a straight-through estimator, where the forward pass uses a one-hot vector, but the backward pass uses the gradients from the soft approximation, which is useful for obtaining discrete samples during inference while maintaining differentiability during training. 3.2. The NRI decoder generative model. The decoder's role is to predict the future states of entities given their initial states and the inferred latent graph structure. It essentially generates the trajectories based on the learned relationships, predicting future states from latent relations. The decoder takes the initial state of the entity's $x_0$ and the sampled latent graph $z$ from the encoder via Gumbel softmax as input. It then iteratively predicts the next state $x_t plus $y based on $x_t$ and the interactions defined by $z$. Decoder message passing. Similar to the encoder, the decoder also uses a message passing scheme, but its purpose is different, to propagate information based on the inferred graph structure. For each entity, it aggregates messages from its neighbors, as defined by $z$, and combines them with its own current state. $m_aj equals \text MLP_\text decoder $, where $z_ij$ is the one-hot encoded relationship type between $i$ and $j$ from the infer graph. These messages are then summed up for each node, integrating with GRU for temporal prediction. The key to the decoder's temporal modeling is the integration of these graph-based messages with a recurrent neural network, typically a GRU. At each time-step code snippet, the decoder 1. Receives the current state of entity's code snippet. 2. Computes graph-based messages using code snippet and the inferred code snippet. 3. Aggregates these messages. 4. Feeds the aggregated messages, along with code snippet, into a GRU cell. 5. The GRU updates its hidden state and outputs the predicted next state code snippet. This allows the decoder to leverage both the explicit relational structure via message passing and the temporal dependencies via the GRU to predict future trajectories. Code example: NRI decoder, message passing and GRU integration. Code is not spoken. To get code, please see the link in description or bio. The code snippet starts by defining MLPs for each edge type, as the interaction message might depend on the infer relationship T. In the code snippet pass, it first computes code snippet for all node pairs. Then, it iterates through each possible code snippet, concatenating the code snippet with the specific one-hot encoding for that edge type. This combined input is fed into the corresponding code snippet to generate messages. Finally, these messages are masked by the code snippet, which is one-hot, to select only the messages corresponding to the active inferred edge type between any pair of nodes. Code is not spoken. To get code, please see the link in description or bio. Following the message computation, code snippet are summed up for each node, aggregating the influence of all active relational messages. This code snippet tensor is then concatenated with the code snippet of the nodes and fed into the code snippet, a code snippet applied independently to each node. The code snippet updates its code snippet, which capture the temporal memory. Finally, encode snippet takes the new hidden states to predict the code snippet, e.g., change in position, which is added to code snippet to get code snippet. This iterative process allows the decoder to roll out predictions over multiple time steps. 3.3. The NRI loss function. The training of the NRI model, as a VAE, involves optimizing a variational lower bound on the log likelihood of the data. This objective typically decomposes into two main components. 1. Reconstruction loss measures how well the decoder predicts the observed data. 2. KL divergence, a regularization term that encourages the inferred posterior distribution over the latent graph to be close to a predefined prior distribution. Reconstruction loss, MSE, for trajectory prediction, The reconstruction loss is often the mean squared error, MSE, between the predicted trajectories and the ground truth trajectories. $\mathgal underscore backslash text reconstruction equals backslash frac 1 t backslash in backslash def backslash something certificate equals 1 caret t backslash something equals 1 caret in backslash hat x underscore I teef backslash caret 2 where backslash hat x underscore I teef is the predicted state of no $I at time $t $x underscore I. T$ is the ground truth state. $T$ is the number of time steps. $and is the number of nodes. And $D$ is the dimensionality of node features. KL divergence for latent space regularization. The KL divergence term ensures that the encoder's inferred posterior distribution $q, Zx, for the latent graph $, does not deviate too much from a simple prior distribution $p, Z, e.g., a uniform categorical distribution over edge types. This regularization prevents the encoder from collapsing into a trivial solution and encourages it to learn a meaningful, interpretable latent space. Backslash mathgal underscore backslash text equals backslash math e underscore zx backslash left backslash log backslash frac q zx backslash right $. 4 discrete latent variables optimized with Gumbel softmax. The KL divergence can be computed analytically or approximated. The prior $p, Z, is often set to a uniform distribution over the possible edge types, meaning each edge type is equally likely a priori. The 2, tau loss is a weighted sum of these two components. Backslash mathgal underscore backslash text total equals backslash mathgal underscore backslash text reconstruction plus backslash beta backslash mathgal underscore backslash textcal where backslash beta is a hyperparameter that balances the importance of reconstruction accuracy versus regularization. Code example: NRI loss calculation. Code is not spoken. To get code, please see the link in description or bio. This code snippet function computes both the reconstruction loss, MSE, and the KL divergence. For the KL divergence, it calculates the posterior probabilities code snippet and their logarithms code snippet from the encoder's code snippet. The prior code snippet is set to a uniform distribution. The KL divergence is then computed per edge and averaged over all edges and the batch. The code snippet hyperparameter allows weighting the importance of the KL regularization. Hyperparameters: Gumbel temperature and prior variance. Gumbel temperature $tau. This hyperparameter in the Gumbel softmax trick controls the softness of the discrete approximation. A higher temperature makes the samples more continuous, while a lower temperature pushes them closer to one-hot vectors. During training, $tau is often annealed, gradually decreased. Over time, starting high to allow for exploration and becoming low to encourage discrete graph structures. Prior variance. In the VE framework, the prior distribution $p, Z, for the latent variable $, is typically chosen as a simple distribution, e.g., a UNIFO. RM categorical distribution for discrete $Z. The variance here refers to the spread or entropy of this prior. A uniform prior, for instance, implies maximum entropy, encouraging the model to explore all possible edge types initially. Choosing a different prior, e.g., one biased towards no edge, could inject domain knowledge but might also constrain the learned graph structures. The KL divergence term ensures that the learned posterior does not stray too far from this chosen prior. By meticulously understanding these internal components and their interactions, one can gain a profound appreciation for how NRI effectively disentangles and models the complex spatiotemporal dynamics inherent in problems like multi-agent pose estimation. Under the hood, recurrent architectures for sequential data. Recurrent neural networks, RNNs, and their more advanced variants, such as gated recurrent units, GRUs, are fundamental building blocks for processing sequential data. Unlike traditional feed-forward neural networks that treat each input independently, RNNs are designed to recognize patterns and sequences by maintaining an internal memory of previous inputs. This memory allows them to leverage information from earlier steps in a sequence to inform predictions at later steps. In the context of the Neural Relational Inference (NRI) model, RNNs and GRUs are crucial for understanding and predicting dynamic relationships between entities over time. While the NRI model uses a specialized, custom GRU for message passing between nodes in a graph, standard RNNs and GRUs are widely employed for general sequential data processing, such as predicting future pose based on a history of joint positions. This section delves into the core mechanics and PyTorch implementations of these powerful recurrent architectures. The basic recurrent neural network, RNN, at its heart, an RNN processes sequences one step at a time, using the current input and a hidden state, its memory of past inputs, to compute the current output and update its hidden state for the next step. This recurrent connection allows information to persist across time steps. The mathematical operations within a simple RNN cell can be summarized as znak podkreślenia te równa się tan w znak podkreślenia te w a jej hh ita według t where $x_t$ is the input at time step $t$. $h_t$ is the hidden state at time step $t$. $h_t, $1 is the hidden state from the previous time step. $_t$ is the output at time step $t$. $W$ and $B$ are learnable weight matrices and bias vectors. $\tan$ is a common activation function. This recurrent nature, where the hidden state feeds back into the network, enables the RNN to model temporal dependencies. Implementing a basic RNN in PyTorch. PyTorch provides a highly optimized code snippet module that encapsulates the complexity of recurrent layers. To integrate an RNN into a larger model, we typically define a class inheriting from code snippet. Let's define a code snippet model, similar to the one used in the NRI context for processing pose sequences. Code is not spoken. To get code, please see the link in description or bio. In the code snippet method, we set up the core components. The code snippet layer is the workhorse, taking code snippet, and code snippet. A crucial parameter here is code snippet. This tells PyTorch that our input tensors will be shaped as code snippet. If code snippet the default, the expected shape is code snippet. For most modern deep learning pipelines, code snippet is more intuitive and aligns with how data is typically batched. The code snippet layer then transforms the RNN's output at each time step into the final desired prediction size. The code snippet method orchestrates the data flow through the network. Code is not spoken. To get code, please see the link in description or bio. Inside code snippet, the initial hidden state code snippet is created as a tensor of zeros. Its shape must match code snippet. It's critical to ensure that code snippet is on the same computational device, CPU or GPU, as the input tensor code snippet using code snippet. The code snippet call processes the entire input sequence code snippet. It returns two tensors, code snippet, the output features for each time step in the sequence, and code snippet, the hidden state for the last time step of the last RNN layer. While code snippet is returned, it's not directly used for the final prediction in this specific code snippet example, as the output code snippet already contains the per time step outputs. The line code snippet applies the final linear layer to a specific slice of the RNN's output. The code snippet slice selects the output features corresponding to the last 10 time steps of the sequence. This indicates that this model is designed to make a prediction based on the most recent history, potentially predicting a future window of 10 time steps. If the goal were to predict only the next single time step, one would typically slice code snippet to get the output from the very last time step. Backpropagation through time, BPT. Training RNNs involves a technique called backpropagation through time, BPT. Conceptually, BPTT is an extension L. Standard backpropagation. Instead of just propagating gradients through layers, it also propagates gradients backward through time, across the recurrent connections. Imagine unrolling the RNN across all time steps of a sequence, effectively creating a very deep feed-forward network. BPT then performs backpropagation on this unrolled network. Gradients are computed for each time step and then summed up. Challenges with BPTT: vanishing and exploding gradients. While powerful, simple RNNs suffer from the vanishing gradient problem and sometimes exploding gradients, especially when processing long sequences. Vanishing gradients. As gradients are propagated backward through many time steps, they can shrink exponentially, becoming too small to effectively update the weights for earlier time steps. This makes it difficult for RNNs to learn long-term dependencies. Exploding gradients. Conversely, gradients can grow exponentially large, leading to unstable training. Gradient clipping is often used to mitigate this. These issues motivated the development of more sophisticated recurrent architectures like long short-term memory, LSTM, networks, and gated recurrent units, GRUs. Gated recurrent units, GRUs, enhancing memory control. GRUs are a simpler variant of LSTMs that address the vanishing gradient problem by introducing gates that regulate the flow of information. These gates allow the GRU to selectively update its hidden state, enabling it to capture long-term dependencies more effectively than a simple RNN. A GRU cell has two main gates. 1. Update gate, $$T$. This gate controls how much of the past hidden state should be carried forward to the current hidden state, and how much of the new candidate hidden state should be incorporated. It's like a merge switch. A value close to 1 means keep the old information, while a value close to 0 means discard the old information and mostly use the new candidate. 2. Reset gate, $$T$. This gate decides how much of the past hidden state to forget. A value close to 0 means forget most of the past when computing the new candidate hidden state, allowing the GRU to effectively reset its memory for new, relevant information. Intuitive analogy for GRU gates. Imagine you're taking notes in a very long lecture. The reset gate is like deciding how much of your previous notes are relevant for understanding the current topic. If the topic dramatically shifts, you might reset your focus and mostly rely on the new information being presented. The update gate is like deciding how much of your current understanding, new information mixed with relevant old information, you want to add to your permanent summary of the lecture. You might keep a lot of old, important points or update them significantly with new insights. These gates, typically implemented with sigmoid activation functions, outputting values between 0 and 1, allow the GRU to learn what information to remember, what to forget, and what new information to incorporate, making it robust to vanishing gradients and capable of modeling longer sequences. Implementing a GRU in PyTorch. PyTorch's code snippet module is used similarly to code snippet. The internal complexity of the gates is handled automatically. Code is not spoken. To get code, please see the link in description or bio. The code snippet class structure and code snippet method are nearly identical to the code snippet because code snippet has the same input-output signature as code snippet. The key difference lies in the internal computations of the code snippet layer, which incorporates the gating mechanisms to manage information flow more effectively. Standard code snippet versus custom GRU implementations. It's important to distinguish between the standard code snippet layer provided by PyTorch and any custom GRU implementations that might have been discussed in earlier sections, e.g., from message passing in the NRI model. Code snippet. This is a highly optimized, general-purpose GRU implementation designed for standard sequential data processing, where inputs are processed time-step by time-step. It's the go-to choice for tasks like time series prediction, sequence classification, and sequence generation when the temporal dependencies are linear or chain-like. Custom GRU, e.g., for NRI in the context of the NRI model, a custom GRU might have been implemented to handle specific graph-based operations, such as aggregating messages from neighboring nodes. While it draws inspiration from the GRU's gating mechanisms, its input structure and how it updates hidden states might be tailored to the graph's topology, e.g., taking inputs from multiple neighbors simultaneously, rather than a single previous time step. These custom implementations are necessary when the problem structure deviates from a simple linear sequence, but they often leverage the core ideas of GRU gates for managing information flow. Both approaches are valid, but they serve different purposes. Code snippet for general-purpose sequence modeling and custom GRUs for specialized architectures that require non-standard recurrent connections. Practical demonstration, end-to-end usage. To solidify understanding, let's create dummy data and demonstrate how to instantiate and run these models, including a minimal training loop. First, a helper function to generate synthetic sequential data. Code is not spoken. To get code, please see the link in description or bio. Running the code snippet model. Code is not spoken. To get code, please see the link in description or bio. Running this code demonstrates that the code snippet correctly processes the code snippet of shapecode snippet and produces encode snippet of shapecode snippet, matching our expectation of predicting 10 future time steps. The code snippet means the RNN has two stacked recurrent layers, where the output of the first layer serves as the input to the second. Running the code snippet model. The process for the GRU model is identical due to the consistent API. Code is not spoken. To get code, please see the link in description or bio. As expected, the GRU model also produces an output of shapecode snippet, accessing the final hidden state code snippet. Both code snippet and code snippet return not only the sequence of outputs, code snippet, but also the final hidden state code snippet of a last layer. While not directly used in the code snippet examples for final prediction, this code snippet can be very useful in other scenarios, such as sequence classification, using the final hidden state as a fixed-size representation of the entire input sequence for classification. Sequence-to-sequence models. The final hidden state of an encoder RNN/GRU is often used as the initial hidden state for a decoder RNN/GRU. Let's modify the code snippet method slightly to show how code snippet could be accessed. Code is not spoken. To get code, please see the link in description or bio. The code snippet will have a shape of code snippet, representing the hidden state after processing the entire sequence for each of the stacked layers. Minimal training loop example. To make these models truly functional, they need to be trained. Here's a basic training loop structure. Code is not spoken. To get code, please see the link in description or bio. This minimal training loop demonstrates the core steps: forward pass, loss calculation, backpropagation, gradient computat, ion, and parameter update. For real-world applications, this loop would be wrapped in a data loading pipeline using code snippet to iterate over datasets in batches. Applications beyond pose estimation. While the code snippet and code snippet models are tailored for pose data, the underlying RNN and GRU architectures are incredibly versatile and applicable to a wide range of sequential data problems. General time series prediction, predicting stock prices, weather patterns, energy consumption, or sensor readings. Natural language processing, NLP. Text generation, generating coherent sentences or paragraphs. Machine translation, translating text from one language to another, often using encoder-decoder RNN/GRU architectures. Sentiment analysis, classifying the sentiment of a review or tweet. Speech recognition, transcribing spoken language into text. Music generation, creating new musical sequences. Reinforcement learning, allowing agents to have memory of past observations and actions. By understanding how RNNs and GRUs process sequential information, you gain a powerful tool for tackling problems that involve temporal dependencies and patterns over time. Temporal adjacency matrices. Dynamic graphs are a crucial concept in modeling real-world systems where relationships and entities change over time. Unlike static graphs, where nodes and edges are fixed, dynamic graphs evolve, with new nodes appearing, existing nodes disappearing, and connections forming or breaking. Examples include social networks, where friendships are made and lost, communication networks where connections fluctuate, or traffic networks where road conditions change. Modeling these temporal dynamics using graph neural networks, GNNs, presents unique challenges. How do we capture the sequence of interactions? How do we represent the state of the graph at different points in time? Two primary conceptual approaches address these challenges: using a single, large temporal adjacency matrix or evolving graph embeddings over time. Approach 1. Representing dynamics with temporal adjacency matrices. One straightforward way to incorporate temporal information into a graph structure is to expand the traditional adjacency matrix to include the time dimension. Instead of having a 2D matrix representing connections at a single snapshot, we create a 3D tensor or a flattened 2D matrix that encodes connections across multiple time steps. This approach effectively flattens the temporal sequence into a single, comprehensive representation. Constructing a temporal adjacency matrix. Consider a simple dynamic graph with a few nodes evolving over a short period. For instance, imagine a network of two friends, A and B, and a new friend C joining. At code snippet, A and B are friends. At code snippet, A and B are still friends, and A becomes friends with C. At code snippet, A, B, and C are all friends. A standard adjacency matrix code snippet for a graph with code snippet nodes is code snippet, where code snippet if nodes code snippet and code snippet are connected, and code snippet otherwise. For a temporal adjacency matrix, we can concatenate the adjacency matrices from each time step. Let's illustrate this with a small Python example. We'll represent each time step's adjacency matrix and then combine them. Code is not spoken. To get code, please see the link in description or bio. This initial code block sets up the basic parameters and defines the adjacency matrix for the first time step, code snippet. We use code snippet for efficient matrix operations. Here, code snippet shows that node A, index 0, and node B, index 1, are connected. Node C, index 2, has no connections. Code is not spoken. To get code, please see the link in description or bio. Moving to code snippet, the network evolves. Code snippet now reflects that node A is connected to both B and C. This demonstrates how new connections are represented over time, specifically C forming a connection with A. Code is not spoken. To get code, please see the link in description or bio. Finally, at code snippet, all three nodes are interconnected, forming a complete graph, a triangle. This code snippet completes our sequence of individual time-step matrices. To form the temporal adjacency matrix, we can stack these individual matrices along a new dimension, creating a 3D tensor. Code snippet. Code is not spoken. To get code, please see the link in description or bio. This block demonstrates how to combine the individual time-step matrices into a single 3D code snippet. The resulting shapecode snippet signifies 3 time steps, each with a 3 by 3 adjacency matrix. This 3D tensor is a direct representation of the dynamic graph over time. Alternatively, for some models or specific GNN architectures, this 3D tensor might be flattened into a larger 2D matrix. For example, if we have code snippet time steps and code snippet nodes, the flattened matrix could be code snippet. This matrix would represent connections between nodes at different time steps, effectively treating each node at each time step as a unique entity. Code is not spoken. To get code, please see the link in description or bio. This final code chunk illustrates a common way to flatten the 3D tensor into a larger 2D matrix. Each code snippet block on the diagonal represents the graph structure at a specific time step. This code snippet matrix can then be fed into a standard GNN, treating the entire temporal sequence as one large, static graph. Connections between time steps, e.g., a node at code snippet influencing itself at code snippet, could be added as off-diagonal blocks if desired, but this simple example. It focuses on within-time step connections, challenges and pitfalls of temporal adjacency matrices. While conceptually simple, using large temporal adjacency matrices presents significant practical challenges. 1. Memory consumption. A graph with code snippet nodes over code snippet timesteps generates a flattened matrix of size code snippet. For even moderately sized graphs, e.g., code snippet, and a reasonable number of timesteps, e.g., code snippet, this matrix will be code snippet. Storing such a dense matrix, which would require 80 gigabytes for float 64 or 40 gigabytes for float 32, becomes prohibitively expensive, quickly exceeding available RAM. Even sparse matrix representations, while more efficient, still incur substantial memory overhead for such large dimensions. 2. Computational complexity. Applying graph operations, e.g., matrix multiplications in GNNs, on such large matrices incurs extremely high computational costs. The complexity of many GNN layers often scales polynomially with the number of nodes, e.g., code snippet or code snippet for dense operations, or code snippet for sparse operations where code snippet is the number of edges. In the flattened temporal matrix, the effective number of nodes becomes code snippet, so operations can scale as code snippet for some code snippet. This makes training and inference on large dynamic graphs impractical. 3. Sparsity. Real-world dynamic graphs are often sparse, meaning most possible connections do not exist at any given time. When concatenating or flattening these matrices, the resulting large temporal matrix will also be highly sparse. While sparse matrix operations can mitigate some computational burden, the sheer scale of the matrix can still be problematic. Furthermore, the majority of the matrix would be 0, representing non-connections, which can dilute the signal for learning meaningful temporal patterns. 4. Limited temporal expressivity. This approach treats the entire temporal sequence as a single, static snapshot. It doesn't inherently model the evolution or causality between time steps, but rather represents a fixed, albeit large, graph. While it can capture patterns within the concatenated structure, it might struggle with long-range temporal dependencies or complex temporal dynamics that are better captured by explicit temporal modeling components. Real-world application. Event sequence analysis. A practical scenario where temporal adjacency matrices could be applied, especially for smaller or less dynamic graphs, is an event sequence analysis, such as analyzing interactions in a short online meeting or a highly localized sensor network. If you need to capture all interactions across a fixed, short duration and treat them as a single, holistic event, this approach can be viable. For example, tracking the sequence of who talked to whom in a 5-minute meeting of 10 people, where each minute is a time step. The resulting code snippet matrix would represent all interactions, allowing a GNN to learn patterns from the entire meeting's social graph. Approach 2. Evolving graph embeddings over time. Given the limitations of large temporal adjacency matrices, a more flexible and scalable approach for dynamic graphs involves modeling the evolution of graph embeddings over time. Instead of creating one giant static graph, this method maintains a dynamic representation of the graph state at each time step. The core idea is to learn a compact, low-dimensional embedding for the graph, or its nodes/edges, at each code snippet, and then use a temporal model to capture how these embeddings change from code snippet to code snippet. Modeling temporal evolution with subcomponents. This approach typically involves multiple sophisticated subcomponents working in tandem. 1. Graph encoder. At each time step code snippet, a standard GNN, e.g., graph convolutional network, graph attention network, processes the graph structure code snippet and its features code snippet to produce node embeddings code snippet. This component captures the structural information at that specific moment. Code snippet code, snippet encoder code, snippet code, snippetage underscore matrix code, snippet code, snippet code, snippet underscore 0, h underscore 1, h underscore code, snippet underscore code, snippet underscore code, snippets underscore code, snippets underscore code, snippet code, snippet code, snippet GRE temporal encoder code, snippet sequence from embeddings code, snippets underscore code, snippets underscore code snippet, tn, caret 2 code snippet t, and embedding underscore dim code, snippet encode snippet t. code, snippet encode, snippet code, snippet encode, snippet code, snippet encode, snippet code, snippet encode, snippet, and T. Caret 2 code, snippet n equals 10. T equals 5 code, snippet 50x, 50 code, snippet encode, snippet code, snippet encode, snippet T individually, rather than their product squared. This is the dominant approach for real-world, large-scale dynamic graphs. Nature of dynamism. Temporal adjacency matrices. Suitable if the temporal aspect is viewed as a fixed, complete sequence where all interactions across time are equally important for a holistic understanding. Less ideal if the goal is to predict future states based on evolving patterns or if the graph changes rapidly. Evolving graph embeddings. Ideal when the goal is to understand and model the evolution of the graph, predict future states, or capture long-range temporal dependencies. If the graph structure changes significantly and continuously, this approach is more robust and flexible. Computational resources. If you have limited computational resources and deal with large dynamic graphs, the evolving embeddings approach is usually the only feasible option due to its superior scalability and efficiency. Beyond these approaches, advanced temporal GNN architectures. While temporal adjacency matrices and evolving graph embeddings represent two fundamental conceptual strategies, the field of temporal graph neural networks, TGNNs, has advanced significantly, offering more sophisticated architectures. These often combine elements of both or introduce NOV-L mechanisms to handle time. Continuous time GNNs, CGNNs instead of discrete time steps. These models handle events arriving continuously in time. They often use techniques like Hawk's processes or neural ordinary differential equations, ODEs, to model event intensities and propagate information through continuous time. Examples include TGN, temporal graph networks, which use message passing on continuous time events. Graph recurrent networks, GRNs. These are an extension of the evolving graph embeddings paradigm, explicitly integrating RNNs, like GRUs or LSTMs, with GNNs. They typically involve a GNN layer at each time step to produce node embeddings, followed by an RNN layer that updates the node's hidden state based on its current embedding and previous hidden state. The NRI model, with its GRU-based encoder, falls into this category. Graph transformer networks. Leveraging the self-attention mechanism of transformers, these models can capture long-range temporal dependencies more effectively than traditional RNNs. They can attend to relevant information across multiple past time steps to inform the current graph state or predictions, offering a more global view of temporal patterns. Dynamic graph representation learning, a broader category that encompasses methods focused on learning dynamic node, edge, or graph-level embeddings that evolve over time, often without explicitly reconstructing adjacency matrices at each step. These methods prioritize learning a continuous, smooth representation of the graph state over time. These advanced architectures build upon the core ideas discussed, providing richer and more efficient ways to model complex temporal dynamics in graph structure data. They represent active areas of research aimed at overcoming the challenges of scalability, expressivity, and real-time processing in dynamic graph analysis. Combining autoencoders with RNNs, the Neural Relational Inference NRI model. The challenge of understanding complex systems often lies not only in predicting their future states, but also in uncovering the hidden relationships that govern their dynamics. Traditional recurrent neural networks, RNNs, excel at temporal sequence prediction, and graph neural networks, GNNs, are adept at modeling interactions on explicit graphs. However, many real-world systems operate with unknown or evolving interaction structures, where neither the graph is given nor a simple RNN can fully capture the intricate relational dynamics. The Neural Relational Inference, NRI, model offers a powerful solution by simultaneously learning the underlying graph structure and predicting the future trajectories of interacting entities. At its core, NRI elegantly combines the strengths of autoencoders, particularly the variational autoencoder (VE) framework, with the temporal modeling capabilities of recurrent neural networks, RNNs, often utilizing gated recurrent units, GRUs. This integration allows NRI to infer a probabilistic latent graph structure from observed spatiotemporal data, and then use this inferred structure to inform future state predictions. Limitations of simple models. Before diving into the NRI architecture, it's crucial to understand why such a complex model is necessary. RNN-only models. While effective for sequential data, pure RNNs, or GRUs/LSTMs, treat each entity's trajectory, IND, independently, or only implicitly learn interentity dependencies through concatenated inputs. They lack an explicit mechanism for relational reasoning. For instance, in a system of interacting particles, an RNN might struggle to predict complex collision dynamics if it doesn't explicitly understand which particles are connected or colliding. It can infer some dependencies, but without a structured representation, this inference is often less robust and harder to interpret, especially as the number of interacting objects increases. GNN-only models with fixed or predefined graph attention networks, GATs, or other GNNs are excellent at processing information on a given graph. Encoder's primary role is to infer the latent interaction graph from the observed spatiotemporal trajectories of the entities. It takes a sequence of node features, e.g., positions, velocities, over several time steps as input and outputs a probabilistic distribution over possible edge types for every pair of nodes. Message passing for latent graph inference. The encoder uses a message passing mechanism to learn relationships. For every potential edge between two nodes code snippet and code snippet, the encoder concatenates their historical features, or a representation derived from their histories, and passes them through a shared multi-layer perceptron, MLP. This MLP outputs logits for code snippet predefined edge types. Consider code snippet entities, each with features code snippet at timestep code snippet. The encoder processes a sequence of features code snippet for all entities. For each pair code snippet, it aims to learn a latent variable code snippet representing their relationship. Code is not spoken. To get code, please see the link in description or bio. This code snippet conceptually represents the core of the encoder's relational inference. It takes the feature vectors of two nodes, which could be derived from their full historical trajectories via another network, e.g., an MLP or RNN for each node, and outputs raw scores, logits, for each possible type of relationship between them. Gumbel softmax for differentiable sampling. The output of the code snippet is a set of logits for code snippet. To sample a discrete edge-type code snippet from this categorical distribution while maintaining differentiability for backpropagation, the NRI model employs the Gumbel softmax trick. The Gumbel softmax function approximates a discrete categorical sample with a continuous, differentiable vector. This allows the gradient to flow through the sampling process, enabling end-to-end training of the VAE. Code is not spoken. To get code, please see the link in description or bio. The code snippet decoder, predicting future trajectories. The decoder takes the inferred latent graph structure, code snippet samples, and the current state of the entities as input. Its goal is to predict the future states of the entities. It achieves this by using a GRU, gated recurrent unit, for each node, where the GRU's input is augmented by messages passed along the inferred edges. Message passing with inferred edges. For each time step, the decoder performs message passing on the inferred graph. For a receiving node code snippet, messages are generated by its neighbor's code snippet based on their current states and the sampled edge-type code snippet. These messages are then aggregated and combined with the receiving node's current state before being fed into its GRU cell. Code is not spoken. To get code, please see the link in description or bio. The first part of the decoder sets up the necessary neural network modules. The GRU cell for temporal dynamics, a list of MLPs for generating messages based on different edge types, and a final MLP to transform the GRU's hidden state into the predicted next state. The code snippet method signature outlines the crucial inputs, including the code snippet, which represent the graph structure learned by the encoder. Code is not spoken. To get code, please see the link in description or bio. This section details the message passing process. For every potential directed edge code snippet, the decoder calculates a message based on the current feature. S of nodes code snippet and code snippet. Crucially, this message is weighted by the probability of the inferred edge type between code snippet and code snippet from the encoder. This means that if the encoder inferred a strong connected relationship, that message will have a greater impact on the receiver node code snippet state update. Code is not spoken. To get code, please see the link in description or bio. Finally, the aggregated messages are concatenated with the node's own current features, forming the input to the GRU cell. The GRU then updates its hidden state, capturing the temporal dependencies under the influence of the inferred relational messages. A final MLP transforms this updated hidden state into the predicted next feature vector for the node. This iterative process allows the decoder to roll out predictions over multiple future time steps. Simultaneous learning and practical applications. The power of NRI lies in its simultaneous learning capability. The encoder infers the most probable graph structure, and the decoder uses that structure to make predictions. The entire model is trained end-to-end using a V-like loss function, which typically includes 1. Reconstruction loss. Measures how well the decoder's predicted trajectories match the true future trajectories. This drives the model to make accurate predictions. 2. KL divergence loss. Penalizes the encoder's inferred latent distribution code snippet for deviating too much from a prior distribute. Tie-encode snippet. Often a simple uniform or Gaussian distribution. This encourages the encoder to learn a meaningful and well-structured latent space, preventing it from collapsing or learning trivial relationships. The concrete distribution and sampling elements mentioned in diagrams directly relate to this VAE framework's reparameterization trick, allowing gradients to flow through the stochastic sampling of code snippet. This coupled learning process allows NRI to discover unknown interaction patterns. Beyond just predicting trajectories, NRI can uncover the rules of interaction. For example, in a simulated team of players, NRI might infer leadership edges or support edges based on movement patterns, even if these roles were not explicitly defined. In a system of particles, it could infer attractive or repulsive forces without prior knowledge. Predict future states more accurately. By leveraging the inferred relational context, the decoder can make more informed and robust predictions than models that ignore or assume the graph structure. Generalized to new scenarios. Once trained, the model can infer relationships and predict dynamics for new sets of interacting entities, even if it hasn't seen those specific interactions before, as long as they adhere to the learned relational principles. NRI's ability to infer hidden relationships and predict dynamic behavior makes it highly valuable in diverse domains. Human pose estimation and prediction. As mentioned, predicting future human movements and understanding how body parts interact. This is critical for robotics, animation, and human-computer interaction. Particle physics and astrophysics. Modeling the trajectories of interacting particles or celestial bodies where the exact forces or connections might be complex or unknown. Biology and chemistry. Analyzing cellular interactions, protein folding dynamics, or molecular dynamic simulations to infer underlying biochemical pathways or binding affinities. For instance, tracking the movement of different cell types in a petri dish could reveal which cells are signaling to each other or forming temporary clusters. Animal behavior analysis. Tracking animal migration patterns within a herd or flock and inferring social structures, leadership roles, or communication networks based on their collective movement and proximity. This could reveal how animals coordinate movements or respond to environmental cues. Traffic flow prediction. Understanding how vehicles interact on a road network, e.g., lane changes, braking, to predict traffic congestion, even without explicit rules for every interaction. By combining the strengths of autoencoders for latent variable inference and RNNs for temporal modeling, NRI provides a powerful framework for tackling complex spatiotemporal problems where the underlying relational dynamics are not explicitly provided, but are crucial for accurate understanding and prediction. Gumbel softmax. Deep learning models, especially those designed to infer underlying structures like the graph connectivity in the neural relational inference, NRI, model, often need to make discrete decisions. For instance, an NRI model might predict whether an edge exists between two entities, a binary choice, or what type of interaction exists, a categorical choice. However, standard gradient-based optimization techniques, such as backpropagation, rely fundamentally on the ability to compute gradients, which requires functions to be differentiable. Discrete operations, by their very nature, are non-differentiable. This presents a significant challenge. How can we train a neural network to output discrete variables while still leveraging efficient gradient-based learning? The challenge of discrete variables in deep learning. When a neural network produces an output that needs to be a discrete choice, like selecting one category out of many or deciding on a binary yes or no, this typically involves a hard thresholding operation, e.g., code snippet for categorical choices or rounding for binary values. For example, if a network outputs probabilities for different categories, code snippet selects the category with the highest probability, resulting in a one-hot vector. Consider a simple neural network producing logits, unnormalized log probabilities, for 3 categories, code snippet. Applying code snippet gives probabilities, code snippet, and code snippet operation on. These probabilities would yield a one-hot vector code snippet, representing the 3rd category. The problem is that the code snippet function is not differentiable. Small changes in the input logits do not produce small, continuous changes in the output. Instead, the output jumps abruptly when the highest logit changes. This makes it impossible to compute gradients and backpropagate error signals through this operation, effectively halting the learning process for preceding layers. To overcome this, we need a way to approximate the discrete sampling process with a continuous, differentiable function. This is where the Gumbel softmax trick comes into play. It allows us to sample from a categorical distribution in a way that is differentiable with respect to its input parameters, the logits, thus enabling end-to-end training of models that infer discrete structures. Understanding the Gumbel softmax function. The Gumbel softmax function provides a continuous and differentiable approximation to sampling from a categorical distribution. It achieves this by introducing Gumbel noise to the input logits before applying the softmax function. This technique is a specific instance of the reparameterization trick, which is crucial for training models involving stochastic, random operations. Mathematical formulation. The Gumbel softmax distribution is derived from the Gumbel distribution, an extreme value distribution often used to model the maximum or minimum of a number of SAM. Please from various distributions. In this context, Gumbel noise helps in picking a category from a set of logits in a differentiable manner. For a set of $k$ logits, $L_1, L_2, \dots, L_k$, outputs of a neural network. The Gumbel softmax sample $I$ for category $I$ is calculated as $. Iligu frat jet I plus tau sum ligu vienas L plus tau $. Here, $1 are the raw logits output by the neural network for each category $I$. $10 are independent samples drawn from a Gumbel distribution $\text Gumbel 0, $1. A common way to sample from $\text Gumbel 0, $1 is by drawing $u\sim\text uniform 0, $1 and computing $g equals $log $log $. Tau is the temperature hyperparameter, a positive scalar that controls the sharpness of the distribution. Let's break down the components. 1. Gumbel noise, $to before applying the softmax. Independent Gumbel noise is added to each logit $. This noise introduces randomness into the selection process, similar to how we might sample from a categorical distribution. 2. Temperature, $tau the sum $L_I plus G for I. Dollar is then divided by $tau. This temperature parameter plays a critical role in shaping the output distribution. 3. Softmax function. Finally, the softmax function is applied to the scale values. This converts the noisy logits into a probability distribution over the categories. The result $y equals y_1, y_2, \dots, y_k$ is a vector of probabilities that sum to 1. Crucially, because the OP rations involved addition, division, exponentiation, logarithm are all differentiable. The Gumbel softmax function is differentiable with respect to the input logits $_. This allows gradients to flow back through the sampling process, enabling end-to-end training. The reparameterization trick in action. The core idea of the reparameterization trick is to separate the random sampling process from the parameters we want to optimize. RS, temperature, and Har parameter. The behavior of the Gumbel softmax function is heavily influenced by its hyperparameters, particularly the temperature $tau and the code snippet parameter. Temperature $tau. The temperature $tau controls how closely the Gumbel softmax output approximates a one-hot distribution. High temperature $tau to empty dollar as $tau increases. The exponent $L_I plus G_I // approaches 0 for all $I. This makes all $1 values approach $1/k, where $k$ is the number of categories, resulting in a nearly uniform distribution. The output becomes softer and more spread out. This encourages exploration in the early stages of training, allowing the model to consider a wider range of possible discrete choices. Low temperature $tau to $0 as $tau approaches 0. The exponent $L_I plus G_I // for the largest $L_I plus G_I term will dominate, while others will become very small. This causes the Gumbel softmax output to become very close to a one-hot vector, effectively mimicking encode snippet operation. The output becomes harder and more concentrated on a single category. This encourages exploitation once the model has learned good representations, focusing on the most probable choice. A common practice is to start with a relatively high temperature and gradually anneal it, decrease it during training. This allows the model to explore the discrete latent space initially and then converge to more precise, one-hot like C. Hoists as training progresses. This annealing schedule helps balance exploration and exploitation. Har parameter, straight-through estimator. During training, we typically use the soft Gumbel softmax output, which is a continuous probability distribution. However, during inference or when we strictly need a discrete, one-hot representation, we might want to convert this soft output into a hard one-hot vector. This is often done by applying code snippet to the soft output. The code snippet parameter in implementations, like PyTorch's code snippet, provides a clever way to achieve this. Code snippet, default for training the function, returns the soft, differentiable Gumbel softmax probabilities. Gradients can flow normally. Code snippet, for inference or specific training scenarios, the function returns a one-hot vector, the hard sample, where the highest probability in the soft Gumbel softmax output is set to 1 and others to 0. Crucially, for backpropagation, the gradients are still computed as if the soft, non-hardened output was used. This is a form of the straight-through estimator, where the forward pass uses the hard, discrete sample, but the backward pass effectively straight-throughs the gradient as if it came from the soft approximation. This allows the model to learn from the hard discrete choice while still benefiting from gradient-based optimization. The distinction is critical. Training. Use code snippet, soft output, to ensure differentiability. Why and allow gradients to flow. In some advanced cases, code snippet might be used with a straight-through estimator to get truly one-hot samples during training while still allowing gradients. Inference/testing. Use code snippet to obtain crisp, one-hot discrete choices, as the model's final output should be a clear categorical prediction. Code demonstration. Gumball Softmax and PyTorch. Let's illustrate the use of code snippet with varying temperature and the code snippet parameter. First, we need to import the necessary PyTorch library. Code is not spoken. To get code, please see the link in description or bio. The code snippet tensor represents the unnormalized log probabilities for 4 different categories. The network would typically learn these logits. Effective temperature, soft samples. Now, let's observe how different temperature values, code snippet, affect the soft, differentiable output of the Gumball Softmax function. Code is not spoken. To get code, please see the link in description or bio. With a high temperature, the Gumball Softmax output is a smooth probability distribution. The values are closer to each other, indicating that the model is less confident or exploring a wider range of possibilities. Code is not spoken. To get code, please see the link in description or bio. As the temperature decreases, the distribution starts to concentrate more around the category with the highest original logit, plus Gumball noise. Code is not spoken. To T-code, please see the link in description or bio. With a very low temperature, the Gumball Softmax output strongly resembles a one-hot vector, with one element very close to 1 and others close to 0. This is the behavior desired towards the end of training when the model should make confident, discrete choices. Effect of code snippet. Hard samples with straight-through gradients. Now, let's see how code snippet affects the output and understand its implications. Code is not spoken. To get code, please see the link in description or bio. When code snippet, the output is a true one-hot vector. This is often used during inference to get a definitive discrete choice, or in advanced training setups where a hard sample is needed in the forward pass, while still allowing gradient flow through the soft approximation in the backward pass. Numerical stability. A minor but important detail in implementations of Gumball Softmax and Softmax in general is ensuring numerical stability when taking logarithms of probabilities. When probabilities are very close to 0, their logarithm approaches negative infinity, which can lead to code snippet, not a number, issues. To prevent this, a small constant, e.g., code snippet, is often added to probabilities before taking their logarithm, or the code snippet function is used directly for better stability. While code snippet handles this internally, it's a good practice to be aware of such considerations when implementing similar functions from S. Cratch. Integrating Gumball Softmax into a model's loss. In the NRI model, the Gumball Softmax output, representing the predicted edge types, is used in subsequent computations. For example, it might be used to weight messages passed between nodes or directly fed into a decoder that reconstructs the trajectories. The loss function then depends on this output. Let's consider a simplified example of how the Gumball Softmax output would be used in a loss calculation, analogous to a variational autoencoder, VAE, setup where discrete latent variables are inferred. Code is not spoken. To get code, please see the link in description or bio. This example shows how the Gumball Softmax output, which is differentiable, can be integrated into a typical deep learning loss function. The gradients from this code snippet would then flow back through the entire network, including the Gumball Softmax layer, allowing the network to learn the optimal logits for predicting the discrete variables. Practical applications beyond NRI. The Gumball Softmax trick, or similar methods for handling discrete latent variables, is not exclusive to the NRI model. It is a powerful technique applicable in various deep learning contexts. Variational autoencoders, VAEs, with discrete latent codes. In VAEs, the latent space is typically continuous. However, for tasks like generating discrete objects, e.g., specific image types, categorical attributes, it's beneficial to have discrete latent codes. Gumball Softmax allows sampling from these discrete latent distributions while maintaining differentiability for training. Reinforcement learning, RL, with discrete action spaces. In many RL environments, agents need to choose discrete actions, e.g., move left, move right, jump. Policy gradient methods often involve sampling actions from a policy network. Gumbel softmax can be used to make this sampling process differentiable, enabling end-to-end training of the policy. Generative adversarial networks, GNNs, with discrete outputs. When GNNs are used to generate discrete data, e.g., text, symbolic sequences, the generator's output needs to be discrete. Gumbel softmax can facilitate training by providing a differentiable approximation to the discrete output layer. Neural module networks. In architectures where different modules are selected based on input, Gumbel softmax can be used to select which module to activate in a differentiable way. In essence, any deep learning architecture that needs to infer or predict discrete categorical variables and requires end-to-end gradient-based training can potentially benefit from Gumbel softmax or similar techniques like the straight-through estimator. Spatiotemporal graph neural networks. A comprehensive recap. The journey through dynamic graphs and spatiotemporal graph neural networks, GNNs, culminates in understanding their indispensable role in modeling complex, evolving systems. Unlike static graphs, which represent fixed relationships, dynamic graphs capture how entities and their interactions change over time. This temporal dimension is crucial for accurately representing and predicting phenomena in the real world, where everything from human movement to traffic flow is in constant flux. The imperative of dynamic graph modeling. Many real-world problems are inherently dynamic, involving entities that interact and evolve over time. Consider a social network where friendships form and dissolve, or a transportation network where traffic conditions fluctuate minute by minute. A static graph, representing a single snapshot, fails to capture this rich temporal information. Spatiotemporal GNNs are designed precisely to bridge this gap, integrating both the structural, spatial, relationships between entities and their temporal dynamics. The necessity arises because interactions are not static. The strength or even existence of a relationship can change. Node states evolve. A person's location, a vehicle's speed, or a stock's price all change over time. Future depends on past dynamics. Predicting the next frame of a human pose requires understanding the sequence of previous movements, not just the current skeletal structure. Representing temporal information in graphs. One of the foundational challenges in spatiotemporal GNNs is effectively encoding time into the graph structure or its features. Temporal adjacency matrices. As previously discussed, a straightforward approach is to represent the graph at discrete time steps using a sequence of adjacency matrices. Each matrix code snippet captures the relationships between nodes at time code snippet. Code is not spoken. To get code, please see the link in description or bio. This simple example shows how a dynamic graph can be conceptualized as a sequence of static graph snapshots. Each code snippet captures the instantaneous connectivity. For more complex scenarios, node features, code snippet, would also evolve over time, providing additional information about the state of each entity. Other approaches and computational considerations. Beyond temporal adjacency matrices, other methods include evolving node/edge features. Graph structure might remain static, but node or edge features change over time. Event-based graphs. Graphs are updated only when specific events occur, rather than at fixed time intervals. Continuous time models. Some advanced models use neural ordinary differential equations, ODEs, to model continuous changes in graph states. However, incorporating the temporal dimension introduces significant computational challenges. Scalability. Storing and processing sequences of large graphs, e.g., thousands of nodes, EDS of time steps, can be memory-intensive. Long-range dependencies. Capturing dependencies over very long sequences is difficult, often leading to vanishing/exploding gradients in traditional recurrent models. Real-time processing. For applications like autonomous driving or real-time robotics, processing dynamic graphs must be extremely efficient. Integrating temporal memory, recurrent neural networks, RNNs. To process sequential data and capture temporal dependencies, recurrent neural networks, RNNs, are indispensable. Unlike feed-forward networks, RNNs possess memory by maintaining a hidden state that is updated at each time step, allowing information from previous inputs to influence current outputs. Gated recurrent units, GRUs, and long short-term memory, LSTM, networks are advanced variants that mitigate the vanishing gradient problem, enabling them to learn longer-term dependencies. Code is not spoken. To get code, please see the link in description or bio. The code snippet tensor from the GRU provides the hidden state for each time step in the sequence, while code snippet represents the final hidden state, encapsulating the memory of the entire input sequence. This mechanism allows the model to understand how node features or graph structures evolve over time. Capturing relational structure, graph neural networks, GNNs. While RNNs handle temporal sequences, GNNs excel at processing data defined on irregular graph structures. They operate by iteratively regating information from a node's neighbors, effectively performing message passing across the graph. This allows GNNs to learn representations that capture the intricate relationships between entities. Graph attention networks, GATs, for instance, learn the importance, attention of different neighbors, allowing them to focus on the most relevant connections. Code is not spoken. To get code, please see the link in description or bio. This GNN layer takes node features in the graph's connectivity, edges as input, and outputs new, enriched node features that incorporate information from their neighbors. This is the spatial part of spatiotemporal modeling. Hybrid architectures, the Neural Relational Inference, NRI, model. The Neural Relational Inference, NRI, model is a powerful example of a hybrid architecture that synergistically combines the temporal modeling capabilities of RNNs with the relational learning power of GNNs. Its core innovation lies in its ability to infer the underlying relational structure, i.e., the graph connectivity, from observed time series data, even when that structure is unknown or latent. NRI operates as an autoencoder. 1. Encoder, RNN plus GNN, it takes sequences of node states as input. An RNN processes the temporal evolution of each node independently. Then, a GNN, often a GT-like structure, is used to infer the latent graph structure between nodes based on their temporal dynamics. 2. Latent graph inference. This is where the magic happens. The encoder learns a distribution over possible discrete graph structures. To make this discrete inference differentiable, NRI employs the code snippet trick, allowing gradient-based optimization to flow through the discrete graph samples. This inferred graph represents the underlying relationships. 3. Decoder, GNN plus RNN, a GNN, e.g., a graph convolutional network, uses the inferred graph structure to pass messages between nodes, generating new node embeddings. These embeddings are then fed into another RNN to predict future node states or trajectories. This architecture is particularly adept at problems requiring out-of-distribution, OD, generalization. By inferring the causal or interaction graph, NRI can generalize to new scenarios or configurations of entities that it hasn't explicitly seen during training, as long as the underlying interaction rules remain consistent. For instance, if trained on a certain number of interacting particles, it can generalize to a different number of particles or different initial conditions, because it has learned the rules of interaction, not just specific trajectories. Code is not spoken. To get code, please see the link in description or bio. This conceptual outline demonstrates how an RNN can first process temporal information, which then feeds into a GNN responsible for inferring relations. Finally, another GNN leverages these inferred relations, and another RNN decodes the future states. This intricate dance between recurrent and graph networks allows NRI to learn complex spatiotemporal dynamics. Pose estimation, a canonical spatiotemporal problem. Pose estimation, the task of determining the configuration of a body, human, animal, or robotic, in space, is a prime example of a problem that benefits immensely from spatiotemporal GNNs. Human pose, represented as a skeleton of joints, is inherently graph-structured, with joints as nodes and bones as edges. Key aspects that make it suitable for spatiotemporal GNNs. Spatial relationships. The fixed connectivity of the skeletal structure, e.g., knee connected to hip and ankle, is a clear graph. Temporal dynamics. Human movement is a continuous sequence of poses. The current pose is highly dependent on previous poses and velocities. Predicting future poses requires understanding these temporal patterns. Complex interactions. Limbs move in coordinated ways. Understanding the interaction between different body parts over time is crucial. Out-of-distribution challenges. People move in diverse and unpredictable ways. A model needs to generalize to novel movements and environments. Spatiotemporal GNNs can capture both the spatial constraints of the skeleton and the temporal fluidity of motion, leading to more accurate and robust pose predictions, even in challenging scenarios like occlusions or rapid movements. Broader applications and future directions. The principles of spatiotemporal GNNs extend far beyond pose estimation, finding utility in a wide array of dynamic systems. Traffic flow prediction. Modeling roads as graphs and vehicles as nodes, predicting congestion patterns. Weather pattern prediction. Graph nodes representing sensor locations, edges representing atmospheric influences. Disease spread modeling. Nodes are individuals or locations. Edges are contact networks, predicting disease propagation. Object trajectory prediction. In autonomous driving, predicting the paths of other vehicles or pedestrians. Social network evolution. Analyzing how friendships, communities, or information spread evolve over time. Fraud detection. Identifying anomalous patterns in financial transactions over time and across related accounts. While powerful, these models face ongoing research challenges, particularly concerning computational efficiency for very large graphs and extremely long sequences. Future work is exploring more efficient graph representations, novel attention mechanisms, and alternative temporal modeling strategies, such as continuous time dynamics, to push the boundaries of what spatiotemporal GNNs can achieve. Understanding the fundamental concepts discussed here provide a solid foundation for delving into these advanced topics and contributing to the next generation of dynamic system modeling.